Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we are going somewhere very small, very strange, and very easy to miss. We're drifting into the heart of matter, past atoms, past nuclei, past the familiar idea that particles are like tiny grains of dust floating in empty space, and towards something far more unusual. A kind of particle that, if it truly exists in the way physicists think it does, is made not from the usual ingredients of matter, but from force itself. A glueball. It sounds almost too playful for a serious object in physics, like something you might find under a school desk or at the bottom of a craft drawer after a particularly ambitious afternoon with paper, glitter and poor supervision. But the name is doing its best. A glueball is, quite simply, what may happen when the force that glues the insides of matter together becomes trapped in a little bundle of its own energy. Not matter held together by a force, exactly, but force holding itself together so tightly that it begins to behave like matter. Now, before we go any deeper, I would love to know where in the world you are listening from tonight. Are you tucked away somewhere quiet with the lights low and the day finally softening at the edges? Are you listening in the morning, perhaps with a cup of tea or coffee nearby, letting the strange world of particle physics gently wake up alongside you? And here is a question to settle into for a moment. When you look around at the ordinary objects near you, your blanket, your pillow, your phone, your glass of water, what do you imagine they are really made of? Not in the everyday sense, not fabric or glass or metal, but deeper down. If you could keep zooming in, past the smooth surfaces and familiar shapes, what would you expect to find waiting at the bottom? Little solid beads, perhaps. Tiny building blocks, something simple, something dependable. Physics, as it often does, smiles politely at that expectation, and then opens a door into a room that is far stranger than the one we thought we were entering. If you find this sort of quiet scientific wandering soothing, or if you enjoy letting the deep workings of the universe become a gentle companion, at the end of the day, I would be ever so grateful if you liked the video and maybe subscribed. It helps this calm little corner of science reach others who might need something peaceful, interesting, and not too loud to rest their minds upon. And as always, I do hope tonight's subject is not so fascinating that it keeps you awake. But if it does, at least you will have spent the evening considering one of the oddest possibilities in nature, that the universe can tie a knot in one of its own forces and make a particle out of it. Which is not a bad thought to have before sleep, provided you do not then try to explain it to your pillow. So settle in, let the room become still. Let the rush of the day step back a little. Tonight's journey begins with something we usually take for granted, the idea that matter is made of matter. That sounds obvious enough. A chair is made of atoms. Atoms have nuclei. Nuclei have protons and neutrons. Protons and neutrons are made of quarks, and quarks are held together by the strong nuclear force. That is the short version, the one that fits nicely into a science textbook, or into the memory of someone who once learned it in school and has been quietly carrying it around ever since. But inside that short version is an enormous mystery, because the strong nuclear force is not just another gentle tug between particles. It is the most powerful of the fundamental forces at the scale where it works. It is the force that keeps quarks locked inside protons and neutrons. It is the force that helps atomic nuclei exist at all. Without it, there would be no stable nuclei, no atoms as we know them, no chemistry, no planets, no warm mugs, no sleepy listeners, and certainly no late-night discussions about glueballs. The strong force is carried by particles called gluons. The name is charmingly direct. They glue quarks together. Physicists are not always known for naming things in a way that sounds cozy, so when they do, it is worth appreciating. Gluons are the messengers of the strong force, passing between quarks, keeping them bound in the small, restless interiors of protons, neutrons, and other particles. But gluons are not like the messengers of some other forces. Light, for example, is carried by photons. Photons do not carry electric charge, so they do not normally pull on one another in the simple way charged particles do. A beam of light can pass through another beam of light without the two beams grabbing each other and forming a little glowing knot. That would be very inconvenient for anyone trying to use a flashlight. Gluons, however, are different. They carry the very kind of charge that the strong force responds to. This charge is called colour charge, though it has nothing to do with red paint, blue blankets, or the slightly suspicious green glow of old science fiction laboratories. It is simply a name physicists use for a property of quarks and gluons. Because gluons carry colour charge, they can interact with each other. They do not merely connect quarks, they can pull on other gluons, they can tangle with them, they can form a dense shifting network of force. That one detail changes everything. It means the strong force is not just a line of connection between bits of matter, it has a life of its own. It can gather, twist and bind. And from this comes the idea of the Glueball. A Glueball would be a particle made entirely of gluons, no quarks inside, no ordinary matter at its core. Just the force carriers of the strong interaction bound together into a compact object. If protons and neutrons are like little rooms where quarks live, with gluons constantly rushing around between them, then a Glueball is more like a room made only of the rushing around, a knot of strong force without the usual occupants. It is a strangely elegant idea, and also a deeply difficult one, because the world inside the strong force is not tidy. It is not like a set of planets orbiting a sun, with smooth paths and clear distances. It is more like an impossibly energetic storm in a space so small that ordinary intuition gives up, sits down and asks for a biscuit. The reason Glueballs matter is not just that they would be exotic, though they certainly are. They matter because they would show us something profound about how reality works. We're used to thinking of forces as things that act on matter. Gravity pulls planets. Electromagnetism lets magnets attract and repel. The strong force holds quarks together. In that familiar picture, matter is the main character, and forces are what matter does to other matter. But a Glueball turns that picture slightly sideways. It suggests that a force field can organise itself into something particle-like. It suggests that what we call matter may sometimes be an expression of energy held in place by rules deeper than our everyday categories. The universe, in other words, may not always bother to separate the actors from the stage. Sometimes the stage itself may ripple into the shape of an actor and wander briefly through the play. That is not mystical language. It is what modern physics has been quietly teaching us for more than a century. In quantum field theory, particles are not tiny hard balls in the old-fashioned sense. They're excitations in fields. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. Quarks are excitations of quark fields. And gluons are excitations of the fields associated with the strong force. Everything we call a particle is, in a very real scientific sense, a little organised disturbance in something more basic. It is just that some disturbances are familiar and stable, while others are rare, brief and very hard to catch. A Glueball would be one of those rare disturbances, a self-bound excitation of the strong force field, a little lump of gluon activity that survives long enough to count as a particle before decaying into more familiar things. This is where the story becomes both beautiful and frustrating. Physicists have expected Glueballs for a long time, because the theory of the strong force allows them, and in many calculations seems almost to demand them. The theory is called quantum chromodynamics, which is a grand name for the rules governing quarks, gluons, and colour charge. It is one of the great achievements of modern physics, and also one of the reasons physicists sometimes look tired. It works extremely well, but it is notoriously difficult to solve in the situations where the strong force becomes strongest. And Glueballs live precisely in that difficult region. They are not expected to be clean little objects that politely introduce themselves. They would appear among many other particles, mix with them, decay into them, and leave traces that are easy to mistake for something else. Looking for a glue ball is a little like trying to identify one particular wave in a stormy sea by listening to the sound it makes after it has already crashed on the shore. The word glue ball itself carries a kind of misleading simplicity. It makes the object sound round, solid, and maybe a bit sticky, as if you could place it on a table beside a marble. But a glue ball would not be a ball in the everyday sense. It would be tiny beyond imagination, unstable and ruled by quantum behaviour. It would not have a surface you could touch or a shape you could draw with much confidence. It would be known through its mass, its spin, its decay patterns, and the way it appears in experiments as a small excess, a resonance, a hint that something formed and then vanished. Particle physics often works this way. It does not catch particles like butterflies in a net. It reconstructs them from what they leave behind, like a detective arriving after a very energetic event and calmly studying the debris while everyone else wonders why the room is full of pions. And yet, despite all the difficulty, the idea remains compelling. There is something deeply satisfying about the thought that force can become matter-like. It reminds us that the categories we use in daily life are helpful, but not final. Matter, energy, force, field, particle. These are not separate boxes stacked neatly on a shelf. They are more like different ways of describing the same underlying activity of nature, depending on where we look and how closely we examine it. At human scale, the difference between a table and the forces holding it together seems obvious. At the quantum scale, that difference becomes more subtle. The table is not simply stuff. It is a pattern maintained by interactions, fields, restrictions, probabilities, and energy. It is stable enough for your cup. That is all everyday life asks of it. But physics asks what makes that stability possible, and the answer leads us into a world where even the glue has its own hidden architecture. To understand a glue ball, we need to become comfortable with the idea that empty space is not really empty, and that the forces of nature are not invisible strings stretched between little beads. The strong force is a field, active everywhere quarks and gluons are involved, and at tiny distances it behaves in ways that are unlike the forces we know from daily life. It grows stronger when quarks are pulled apart, almost as though nature refuses to let them wander off alone. Try to separate two quarks, and instead of getting isolated quarks, you put so much energy into the field between them that new particles can appear. It is like pulling on an elastic band that does not simply snap, but produces more tiny bands, more knots, more complications. The universe at this level is not especially interested in making things easy for anyone with a diagram. This refusal to let quarks roam freely is called confinement. It is one of the central features of the strong force, and it is why we do not see lone quarks drifting around the room, which is probably for the best. Confinement means that quarks are locked inside larger particles, bound together by gluons in combinations that are allowed by the rules of color charge. But if gluons interact with each other, then confinement may also allow gluons to bind into combinations without quarks. This is the quiet doorway through which the glue ball enters. Not as an afterthought, not as a piece of science fiction, but as a natural possibility created by the same rules that make protons and neutrons possible. It is worth pausing here, gently, because this is the central strangeness of the whole subject. The strong force does not merely glue matter together. Under the right conditions, it may create its own particle-like structures. The binder can bind itself. The messenger can become the message. The field can gather into a thing. And the thing, if we can ever identify it clearly, would be one of the purest examples we have of force taking on the role we normally reserve for matter. That does not mean it would last forever. Most exotic particles in high-energy physics live for tiny fractions of time, far shorter than a blink, shorter than a thought, shorter than the time it takes to regret checking your phone after getting comfortable in bed. But brief does not mean unreal. In particle physics, many real things are fleeting. They are known not by how long they stay, but by the consistency of the traces they leave. So tonight, as we begin this slow walk into the hidden world of glue balls, we're really beginning with a question about what counts as matter. Is matter only what is made from quarks and electrons? the familiar ingredients of atoms? Or is matter a broader kind of behaviour? Any stable or semi-stable pattern of energy that carries mass responds to the laws of physics and can be detected through its effects. A Glueball pushes us toward the broader view. It tells us, or at least suggests, that the universe is more flexible in its construction than our everyday language implies. It does not always build things from tiny bricks. Sometimes it builds from tension, interaction, and trapped energy. Sometimes, deep in the quantum world, what holds other things together may briefly hold itself. And that is where our path leads next, into the invisible glue that sits inside every proton and neutron, working so steadily that the ordinary world depends on it while almost never noticing it is there. Before a Glueball can make sense, the glue itself has to become familiar. Not familiar in the sense that we can picture it perfectly, because no one can really picture the strong force in the way we picture a chair or a falling apple, but familiar enough that its strangeness begins to feel less like a wall and more like a doorway. The objects around you, quiet and solid in the room, owe their existence to a force that is anything but quiet. And if we listen closely to what that force is doing, we begin to see how the idea of a Glueball is not an odd decoration added to physics, but a natural consequence of the restless machinery inside matter itself. Before we can understand how a Glueball might form, we need to spend a little time with the glue itself, not the kind tucked away in a drawer, slowly drying in its cap while everyone pretends it is still usable, but the invisible force that holds the cores of atoms together. This force is so essential that every object around you depends on it. Your blanket, your hands, the walls, the air moving quietly through the room, the tiny minerals in a cup of tea, all of it is built on structures that would fall apart without the strong nuclear force. It does not announce itself in daily life. You cannot feel it directly in the way you feel gravity pulling you into a chair, or magnetism tugging a paperclip toward a fridge magnet. It does not appear as a spark, a glow, or a breeze. It works in a hidden place, inside the atomic nucleus, on distances so small that ordinary imagination has to take very tiny steps and still gets tired before arriving. The strong nuclear force is one of the 4 fundamental forces of nature. Gravity shapes planets, stars, and galaxies. Electromagnetism governs light, electricity, magnetism, chemistry, and almost everything your senses can directly notice. The weak nuclear force is involved in certain kinds of radioactive decay and in the reactions that help stars shine. And then there is the strong force, the quiet powerhouse of the subatomic world. It is the force that binds quarks together inside protons and neutrons, and it also helps bind protons and neutrons together inside atomic nuclei. Without it, atoms would not have stable centers. Without stable centers, atoms as we know them would not exist. And without atoms, the universe would be a rather thin and uneventful place, with very little opportunity for mountains, oceans, biology, biscuits, or anyone lying in bed wondering what a Glueball is. At first glance, the need for such a force may not seem obvious. We often learn that atoms have a nucleus made of protons and neutrons, with electrons arranged around it. That picture is already simplified, but it is useful enough for a first look. The trouble appears when we remember that protons carry positive electric charge. Positive charges repel one another. Put 2 protons close together, and electromagnetism says they should push apart. Put many protons together inside a nucleus, packed into a space far smaller than the atom itself, and the repulsion should be enormous. Every nucleus heavier than hydrogen is basically asking a dangerous question. How can a cluster of positively charged particles sit together without flying apart, like people suddenly realizing they're all standing too close in a very small lift? The answer is that another force is at work, and at those tiny distances it is stronger than the electromagnetic repulsion. This is the nuclear binding side of the strong force. It acts between protons and neutrons, holding the nucleus together tightly enough for atoms to remain stable. It is not a long-range force like gravity or electromagnetism. It does not reach out across rooms, planets, or star systems. It works over incredibly short distances, roughly the scale of an atomic nucleus. At that scale, though, it is astonishingly powerful. It is like a very determined caretaker, keeping the nucleus from becoming a tiny explosion of disagreement. But the story does not stop with protons and neutrons. In fact, that is only the outer layer of the mystery. Protons and neutrons are not fundamental particles in the same way electrons appear to be. They are composite objects. Each one is made of quarks, and those quarks are bound together by the strong force in its deeper form. If atomic nuclei are held together by a kind of leftover strong interaction between protons and neutrons, then inside each proton and neutron we find the stronger and more direct version of the force, the one carried by gluons. This is where the name Glueball begins to make more sense. Gluons are the force carriers. They are the particles associated with the strong interaction, passing between quarks and holding them in place. If quarks are the inhabitants of the proton, gluons are the restless connections between them, the ceaseless activity that makes the whole object possible. It is tempting to imagine a proton as a small container with 3 quarks sitting neatly inside, perhaps arranged like peas in a pod, while gluons politely link them together like bits of string. This picture is tidy, which is exactly why nature refuses to behave that way. A real proton is not a quiet little box containing 3 still objects. It is a turbulent quantum system. The quarks inside are constantly interacting. Gluons are being exchanged. Short-lived pairs of quarks and antiquarks appear and vanish in the restless field. The interior of a proton is less like 3 marbles in a bag, and more like a tiny storm of fields and energy, with the recognizable quarks emerging as part of the pattern. If that sounds difficult to picture, that is not a failure of imagination. It is a sign that you are paying attention. The inside of matter is not built to fit comfortably into furniture-based metaphors, though we keep trying because furniture has been good to us. The strong force is described by a theory called quantum chromodynamics. The name sounds grand, and it is. It is the theory of quarks, gluons, and the charge they respond to, called color charge. Color charge is not actual color. A quark is not red in the way a strawberry is red, and a gluon is not blue in the way a quiet evening sky may be blue. Color is simply a label physicists use to describe a type of charge involved in the strong interaction. The word was chosen because the rules for combining these charges have a loose resemblance to the way colors can combine in human language, though the resemblance should not be pushed too far. As with many things in physics, the name helps until it does not, and then it must be gently set down before it gets into trouble. Color charge is the key to why the strong force behaves so differently from electromagnetism. In electromagnetism, electric charges interact by exchanging photons. Photons themselves do not carry electric charge, so in ordinary conditions they do not pull directly on each other. Gluons, however, carry color charge. That means gluons can interact with other gluons. The force carrier is itself affected by the force it carries. This one fact gives the strong interaction much of its unusual character. It is also the reason glueballs become possible. If gluons can pull on one another, then a collection of gluons may be able to bind itself into a particle-like object without needing quarks as the main ingredients. Before arriving there, though, we should let the behavior of the strong force become clearer. One of its strangest features is confinement. Quarks do not appear alone in nature under ordinary conditions. You never find a lonely quark drifting through a detector, like a tiny lost traveller asking for directions. Instead, quarks are always confined inside larger particles such as protons, neutrons, and other hadrons. If you try to pull quarks apart, the energy in the strong field between them grows. It does not weaken in the familiar way you might expect from gravity or electromagnetism. With those forces, distance usually softens the interaction. Move 2 magnets apart and their pull fades. Move 2 planets farther apart and gravity becomes weaker. But with quarks, trying to separate them is more like stretching a very stubborn band of energy. The farther you pull, the more energy you store in the field, until eventually there is enough energy to create new particles. Instead of isolating a quark, you end up making more hadrons. Nature keeps the quarks hidden, rather like a parent cleaning up toys by putting them in smaller boxes that somehow contain more toys. This confinement is one of the great reasons ordinary matter is stable. Protons and neutrons stay intact because quarks cannot simply wander away. But confinement also makes the strong force hard to study. When physicists collide particles at high energies, they do not see free quarks or free gluons directly. They see jets of ordinary hadrons produced as quarks, and gluons transform into allowed combinations. The fundamental players leave the stage before the audience can see them clearly. The detector records the aftermath, and scientists reconstruct the event from patterns in the debris. Particle physics is often a careful study of endings used to infer beginnings. It is a little like hearing a crash in the kitchen and then determining from the broken plate, the missing biscuit, and the guilty expression of a cat what must have happened. Another unusual feature of the strong force is that it becomes weaker at very short distances or very high energies. This is called asymptotic freedom. The name sounds like a very serious philosophical retreat, but the idea is concrete. When quarks are extremely close together, they behave almost as if they are free. When they move farther apart, the strong force grips them more tightly. This is the reverse of what everyday intuition expects. It means that inside a proton, at very small scales and high energies, quarks can act somewhat freely for brief moments, but they remain trapped overall by the confining nature of the strong interaction. The proton is therefore both restless and stable, full of motion, yet persistently itself. In that sense, it is not unlike someone trying to fall asleep while remembering 3 things they forgot to do. This combination of freedom at short distances and confinement at larger subatomic distances makes the strong force exceptionally rich. It also makes it mathematically challenging. For some physical situations, quantum chromodynamics can be handled with techniques that work beautifully when the interaction is weak enough. But when the force becomes strong, especially in the region where particles like glueballs would exist, ordinary calculation methods become difficult. Scientists often turn to powerful computer simulations, including an approach called lattice quantum chromodynamics. In that method, space and time are represented as a kind of grid, and the behavior of the strong force is calculated step by step. It is not a simple task. It requires immense computing power and careful interpretation, but it has provided some of the strongest theoretical reasons to expect glueballs. The same theory that explains why quarks are confined also predicts that gluon fields can form bound states. In a simplified world containing only gluons and no quarks, glueballs appear naturally in calculations. They are not an odd extra idea pasted onto the theory. They emerge from the rules. The complication in the real world is that quarks do exist, and particles made from quarks can have the same overall properties as glueballs. That means a real glueball may mix with ordinary mesons, which are particles made from a quark and an antiquark. The result is not always a pure object wearing a name tag. It may be a blend, part gluonic, part quark-based, with its identity spread across several observed particles. This makes the search difficult, but it also makes the strong force more interesting. Nature rarely labels things for our convenience. If it did, physics conferences would be much shorter, though perhaps less dramatic. To appreciate why the strong force is so central, it helps to remember that most of the mass of familiar matter does not come from the bare masses of quarks themselves. The quarks inside protons and neutrons are relatively light compared with the particles they form. Much of the mass of a proton or neutron comes from the energy of the strong field and the motion and interactions inside. In other words, the mass of ordinary matter is largely tied to the dynamic energy of the strong force. That means the strong force is not merely a hidden glue holding pre-existing heavy pieces together. It is deeply involved in producing the mass of the matter around us. Your hand resting on the blanket is made of atoms, whose nuclei contain protons and neutrons, whose mass is mostly the energy of confined quarks and gluons. The solidity you feel is shaped by electromagnetism between atoms, yes, but the weight and substance of the atomic nuclei trace back in large part to the strong force. That is a humbling thought. Much of what feels like solid stuff is energy held in a disciplined quantum pattern. The universe, as usual, has been doing something extravagant while looking perfectly ordinary. The strong force also plays a major role in stars. In the cores of stars, nuclear fusion changes one kind of nucleus into another, releasing energy that eventually becomes starlight. The details involve several forces, including the weak force and electromagnetism, but the binding of nuclei is governed by the strong interaction. The energy released by stars depends on the differences in nuclear binding. Every warm patch of sunlight on your skin carries a distant connection to the force that holds nuclei together. The same invisible glue that keeps atomic centers intact also helps make possible the long lives of stars, the formation of elements, and the chemical richness of the universe. It is not an exaggeration to say that the strong force sits quietly behind the existence of carbon, oxygen, iron, and the many ingredients from which planets and living things are built. It is not usually the force that appears in poems, postcards, or weather reports, but it has earned its place in the background. There is a delicate balance here. If the strong force were much weaker, atomic nuclei might not hold together properly. If it were much stronger, nuclear reactions and element formation could be very different. The universe we inhabit depends on the particular behavior of this force. It holds quarks tightly, but allows the right kinds of nuclear transformations. It binds nuclei, but only across short distances. It is powerful, but not everywhere. Local, but essential. Hidden, but responsible for much of the visible world. In a way, the strong force is like the quiet structural work inside a building. You may admire the windows, the furniture, the warm lamp in the corner, but none of it would remain in place without beams you rarely notice. For a subject called the strong force, it has a surprisingly shy public life. Gravity receives endless attention because it shapes falling apples, tides, orbits, and black holes. Electromagnetism is everywhere in daily technology, from screens to lights to the chemistry of taste and touch. The weak force, while less familiar, has a certain mysterious reputation thanks to radioactivity and the inner workings of the sun. But the strong force stays mostly tucked away inside matter. We do not have strong force batteries, strong force lamps, or strong force fridge magnets. We cannot casually switch it on and off. It is too short-ranged and too deeply confined within particles and nuclei. To study it directly, scientists need particle accelerators, detectors, and mathematical tools of great subtlety. The strong force is not less important because it is hidden. It is hidden because it is doing work in the most compact rooms nature has. The idea of invisible glue can be misleading if we imagine something passive, like paste holding paper together. The strong force is not a simple adhesive. It is an active quantum field, full of interactions. The word glue is helpful because it captures the binding role, but it does not capture the motion, the self-interaction, the confinement, the energy, the constant exchange of gluons. Inside a proton, gluons are not little strips of tape. They are the carriers of a dynamic field. They can be emitted and absorbed. They can interact with each other. They can contribute to the energy and structure of the particle. The proton is not glued together once and then left alone. It is continuously maintained by the activity of the strong interaction. It is less like a finished sculpture and more like a whirlpool that keeps its identity while water moves through it. Though even that image is too gentle because the quantum world is not water and protons are not politely swirling in a garden pond. This matters for glueballs because a force that is active in this way may have its own forms of organization. If gluons were merely simple messengers that did not interact with one another, glueballs would not be expected. But because gluons carry color charge and feel the strong force, they can form configurations with other gluons. The field can bind itself. That is the key step from ordinary nuclear glue to a glue ball. The same invisible mechanism that helps build the matter we know may also create particles made from its own carriers. It is as though the scaffolding of matter can briefly become the building. Not in a magical sense, but through the rules of quantum fields. There's another reason the strong force feels so strange compared with our everyday expectations. In daily life, we usually separate objects from interactions. A book sits on a table, the table supports the book. A magnet pulls a pin, the pin moves toward the magnet. We think of things first, forces second. But in modern particle physics, things and interactions are more deeply interwoven. A proton is not simply 3 quarks plus a little binding, it is the whole interacting system. Remove the strong force, and the proton is not merely loosened. It stops being a proton in any recognizable way. The force is part of the identity of the particle. The interaction is not an accessory, it is structure. This is one of the quiet lessons hidden in the study of glue balls. The universe may not be made of tiny objects that then happen to interact. It may be made of fields whose interactions create the objects we observe. Some of those objects are familiar and long-lived. Others are brief and exotic. But all are patterns in physical fields. The strong force gives us one of the clearest and most dramatic examples of this idea because it is so self-involving. Gluons make the force, feel the force, and may bind through the force into new states. There is a kind of closed loop there, not a paradox but a deep feature of the theory. The glue has glue. Physicists study this not because it is charming, although it is, in a very specialized way, but because it tests our understanding of the strong interaction. Finding a glue ball, or identifying which observed particle has a large glue ball component, would tell us that quantum chromodynamics is working in one of its most difficult and revealing regimes. It would confirm that gluon fields can form bound states without quarks as the primary structure. It would help explain the spectrum of particles seen in high-energy experiments, and it would deepen our understanding of how mass and matter emerge from fields. A glue ball is not just a curiosity sitting in a corner of the particle zoo. It is a test of whether we truly understand the invisible glue that makes ordinary matter possible. For now, it is enough to hold on to this picture. Deep inside atoms, inside the protons and neutrons that form nuclei, quarks are bound by gluons. Those gluons carry the strong force, but unlike photons in ordinary electromagnetism, gluons also interact with each other. This makes the strong force powerful, self-interacting and confining. It makes quarks impossible to isolate under ordinary conditions. It gives protons and neutrons much of their mass through the energy of the fields inside them. It allows atomic nuclei to exist. It helps stars shine and elements form. And because the glue can interact with itself, it opens the door to a particle made mostly or entirely of that glue. So when we speak of a glue ball, we're not starting from a silly name and trying to make it serious. We are following the strong force to one of its natural conclusions. The universe contains a field that binds quarks together. The carriers of that field can bind each other. Under the right conditions, that binding may produce a short-lived particle-like state, not made of ordinary quark matter, but of the strong force itself. Before we meet that object more directly, though, it helps to look more closely at the gluon, this strange messenger that does not merely carry a force from place to place, but participates in the very force it carries. Because once the gluon enters the story properly, the path toward force becoming matter becomes clearer, and also a little more wonderfully unreasonable. Now that the strong force has stepped into the room, quietly but with the strength to hold the visible world together, we can turn toward one of its most peculiar little workers, the gluon. It is a small word for a deeply strange thing. In ordinary language, it sounds almost friendly, almost practical, like a tiny tube of glue with good intentions and a very specific job. In physics, though, the gluon is not a sticky droplet and not a little hook fastening particles together. It is the carrier of the strong interaction, the restless messenger that moves between quarks, allowing them to bind into protons, neutrons, and many other particles that appear briefly in high-energy experiments before vanishing into more stable company. If quarks are the familiar characters inside the proton, then gluons are the constant conversations between them. They are not simply passing notes, they are the reason the conversation exists at all. The first thing to say about gluons is that they belong to a world where our ordinary pictures begin to wobble. We like to imagine particles as tiny specks, because the human brain is fond of specks. Dust on a shelf, grains of salt, crumbs that somehow appear in bed even when no one admits to eating toast there. Specks make sense to us. But a gluon is not a speck in the everyday sense. It is a quantum of the strong field, a packet of activity associated with the force that binds quarks. That may sound a little slippery, and it is. Modern physics does not describe the deepest known ingredients of nature as miniature pebbles floating in a void. It describes them through fields, and particles are what appear when those fields become excited in particular ways. A gluon is one of those excitations. It is not a tiny bead carrying glue. It is the strong force becoming active in a detectable, transferable form. Still, the messenger picture is useful if we treat it gently. Forces in quantum physics can be described through the exchange of particles. Electromagnetism is carried by photons. The weak force has its own heavy messenger particles. The strong force is carried by gluons. When quarks interact through the strong force, gluons are exchanged between them. But this exchange is not like two people tossing a ball across a garden. It is more subtle than that, because the quantum world does not arrange itself into tidy little scenes with clear before and after moments. The exchange is part of the mathematical structure of the interaction. It is how the force expresses itself. If that feels hard to visualize, that is perfectly all right. Even physicists often rely on diagrams that are not literal pictures, but careful bookkeeping tools for processes too strange to sketch in the usual way. The gluon gets its name because it glues quarks together. That much is refreshingly direct. Quarks are never found alone under ordinary conditions. They are always bound into larger particles, and gluons are responsible for the binding. A proton contains quarks, but it is not merely quarks. It is full of gluon activity. The same is true of the neutron. In fact, if you could somehow look inside a proton with enough resolution, not with a microscope of course, because that would be like trying to weigh a whisper with a bathroom scale, you would not see three calm quarks sitting in a neat triangle. You would find a turbulent dynamic system. Quarks, gluons, and fleeting quark and antiquark pairs would all be part of the restless quantum interior. The gluons would not be decorative. They would be central to the structure, the energy, and the mass of the proton. This brings us to one of the most important ideas in this whole subject. A gluon carries a type of charge called color charge. The name color is a bit mischievous, because it has nothing to do with visible color. No one has painted the quarks red or green or blue, and a gluon does not glow like a tiny festive light. The word color is a label, chosen because the way these charges combine reminded physicists loosely of color mixing. It is a metaphor, and like most metaphors in physics, it should be allowed to help for a while, and then politely asked not to overstay its welcome. Color charge is simply the kind of charge involved in the strong force, just as electric charge is involved in electromagnetism. Quarks carry color charge and gluons respond to it. That is the foundation of the strong interaction. But here is where gluons become especially interesting. Gluons also carry color charge themselves. This makes them very different from photons, the carriers of electromagnetism. Photons do not carry electric charge, so they do not normally interact directly with one another. Shine two flashlight beams across the same room, and they pass through each other without forming a glowing traffic jam in the middle. Gluons are not so aloof. Because they carry the very charge that the strong force acts on, gluons can interact with other gluons. They can tug on each other, scatter from each other, and contribute to the structure of the field that binds quarks. This self-interaction is one of the deep reasons the strong force behaves in such unusual ways. A simple force carrier would be strange enough. A force carrier that feels its own force is something else entirely. It is like a messenger who not only delivers letters between houses, but also writes new letters, blocks streets, builds bridges, and occasionally becomes part of the neighbourhood architecture. The gluon is not a passive courier. It participates in the strong field. It helps create the very environment through which it moves. This makes the inside of a proton enormously rich. The quarks are not just connected by quiet lines of attraction. They are immersed in a field where gluons are constantly interacting, branching, recombining, and shaping the energy of the whole system. It is not an empty room with a few threads stretched across it. It is more like a busy kitchen, where every spoon is also cooking, every kettle is also giving instructions, and somehow, despite all this, breakfast still arrives. The colour charge carried by gluons also explains why the strong force is so deeply different from forces we meet in daily life. Electromagnetism can reach across large distances, growing weaker as objects move apart. Gravity also reaches across the universe, faint but persistent, pulling moons around planets and planets around stars. The strong force is short-ranged. It acts powerfully inside protons, neutrons, and nuclei, but it does not extend outward in the same free way. The reason has to do with confinement, the same feature we touched on earlier. Colour-charged particles cannot be isolated as free objects under ordinary conditions. Quarks are confined, and gluons are confined too. A lone gluon does not fly across a room and strike a detector like a free photon. It is trapped within the world of hadrons, the family of particles made from quarks, antiquarks, and gluons. When high-energy collisions produce quarks or gluons, they quickly transform into sprays of colour-neutral particles. We see the shower, not the original free colour-charged object. That phrase, colour-neutral, is worth settling into for a moment. The strong force allows combinations of colour charge that cancel out in a particular way, producing particles that can exist independently. Protons and neutrons are colour-neutral overall. Mesons, which are made from a quark and an antiquark, are also colour-neutral overall. The universe seems to insist that anything travelling freely must hide its colour charge inside a balanced combination. It is as though nature allows the strong force to be wildly active indoors, but demands that anything leaving the house be properly dressed. This is why quarks and gluons do not appear as isolated particles in detectors. They dress themselves in hadrons almost immediately, and physicists must infer their presence from the patterns left behind. The gluon, therefore, lives a curious life. It is fundamental in the theory, essential to the structure of matter, and yet never seen alone. It is everywhere inside the particles that make atoms possible, but absent as a free object in ordinary experience. It helps create most of the mass of protons and neutrons, but it's not something you can place on a scale by itself. It is one of the most important ingredients in the universe, and also one of the most hidden. There is something almost modest about that, although modest may be the wrong word for a particle associated with the most powerful force at small distances. Perhaps it is more like someone doing all the hard work backstage while the quarks take the curtain call. There are different types of gluons, though the word type should be handled carefully. In the mathematical description of the strong force, gluons come in several varieties associated with different combinations of colour and anti-colour. We do not need the technical details here, and we certainly do not need to turn bedtime into a chalkboard. What matters is that gluons can change the colour charge of quarks as they interact with them. A quark can emit or absorb a gluon and emerge with a different colour charge, while the total colour structure is conserved. This constant reshuffling is part of how quarks remain bound. The strong interaction is not a static connection. It is a continuous exchange and rearrangement of colour charge, a kind of quantum bookkeeping so active that the word bookkeeping suddenly feels far too sleepy for what is going on. If you could listen to the interior of a proton, Not with ears, of course, but with some impossible instrument tuned to quantum fields, it would not sound like a calm hum. It would be more like a storm of interactions at a scale where time and space are measured in ways far removed from human senses. Gluons would be appearing in the mathematics as carriers of exchanges, forming loops, contributing to the energy, pulling the quarks into confinement, and interacting among themselves. The proton is stable, but it is not still. It endures because of motion, not because of rest. That is a lovely little reversal. The particles that make stable matter are themselves sustained by ceaseless activity. The chair is quiet because its deepest ingredients are not. This hidden activity is also why the mass of ordinary matter is not simply the sum of small ingredient masses. The quarks inside a proton have their own masses, but those masses account for only a small part of the proton's total mass. Much of the rest comes from the energy of the strong field and the motion of the quarks and gluons inside. When people say that energy and mass are related, this is one of the places where that idea becomes very concrete. A proton is heavy largely because of the energy of the confined strong interaction within it. The gluons are not optional decoration. They are responsible for much of what makes matter feel substantial. Your body, your pillow, the floor beneath you, all owe a great deal of their mass to the energetic dynamics of gluons inside protons and neutrons. It is a strange comfort, perhaps, to know that what feels solid is partly the result of a very tiny, very disciplined storm. The gluon also helps explain why particle collisions at high energies produce such complicated sprays of matter. When quarks or gluons are knocked loose in a collision, they cannot remain alone. The strong field between colour-charged objects stores energy as they separate. Eventually that energy becomes new quark and antiquark pairs, which combine into hadrons. This process creates jets, narrow sprays of particles that reveal the direction and energy of the original quark or gluon. In experiments, gluons are often identified through these jets. A gluon jet can have different patterns from a quark jet, because gluons carry colour charge in a different way and tend to radiate more strongly. Again, physicists do not see a lone gluon. They see its consequences, like footprints in snow after the traveller has already gone indoors for tea. The discovery of gluons was not a simple matter of seeing one directly. Their existence was confirmed through patterns in high-energy particle collisions, especially events where the debris revealed the presence of an extra spray consistent with gluon radiation. This was one of the triumphs of modern particle physics. The theory predicted that if quarks interact through gluons, then under the right conditions a quark could radiate a gluon, producing a distinctive event pattern. Experiments saw those patterns. The invisible messenger had left a visible trail. It is a nice example of how physics often works. We do not always catch nature in the act. Sometimes we catch the shape of what must have happened, repeated again and again until the conclusion becomes hard to avoid. Once gluons were established, the strong force became clearer but also more mysterious. Clearer because quantum chromodynamics gave physicists a powerful theory for quarks and gluons. More mysterious because the theory revealed how difficult strong interactions can be when the force is truly strong. The self-interaction of gluons is mathematically beautiful and physically rich, but it also makes calculations hard. In some situations, when quarks are very close together and the interaction is effectively weaker, physicists can calculate with great precision. In other situations, especially where confinement dominates, the calculations become far more difficult. That is the territory where glueballs are expected to live. They belong to the world where gluons are not just messengers exchanged between quarks, but active participants capable of forming bound states. This is the point at which the gluon begins to look less like a supporting character and more like the beginning of a mystery. If gluons can interact with each other, and if the strong force confines colour charge, then why should gluons only exist as binding material between quarks? Why could the field not gather into a colour-neutral bundle made only of gluons? The theory says it can. A glueball would be just such a bundle, at least in its cleanest imagined form. It would be a particle-like state made from gluons without valence quarks inside. That phrase, valence quarks, simply means the main quark ingredients that define many ordinary hadrons. A proton has 3 main quarks. A meson has a main quark and antiquark. A glueball, by contrast, would have no such main quark skeleton. Its identity would come from gluons. The idea feels strange because we are used to thinking of force carriers as things that connect matter, not as things that become matter like themselves. But the gluon was never a simple connector. It carries color charge. It interacts with itself. It contributes energy and mass. It lives inside confined systems. It can form rich field patterns. So the leap to glueballs is not a wild leap into fantasy. It is more like following the logic of the gluon all the way down the corridor and discovering that the corridor has a very small, very interesting door at the end. There is a gentle danger here, though. We should not imagine glueballs as little bags filled with gluons in the same way a jar might be filled with marbles. Quantum particles are not assembled like craft projects. A glueball would be a bound state of the gluon field, a pattern of excitations with certain measurable properties. The number of gluons inside may not be fixed in the simple way we might expect. Quantum fields allow processes where particles can appear and vanish as part of the internal structure, provided the overall rules are respected. So even saying a glueball is made of gluons is a useful simplification, not a complete picture. But it is still meaningful. It distinguishes the object from particles whose primary structure is based on quarks. It points to the central idea that the strong field can organize itself without the usual matter ingredients. The gluon's role as the tiny messenger of color is therefore double-edged. It explains the familiar stability of matter, and it opens the door to unfamiliar forms of matter. It keeps quarks confined inside protons and neutrons, and it may also bind with other gluons into exotic particles. It is hidden from direct view, but its effects shape everything from the mass of the proton to the jets seen in particle detectors. It is not colourful in the ordinary sense, yet colour charge is the language through which it acts. It is massless as a fundamental carrier in the theory, yet the energy of gluon fields helps produce massive particles. It is, in a quiet way, one of nature's great reminders that small things need not be simple. Perhaps the most helpful way to think about the gluon tonight is not as a tiny object, but as a rule made active. It is the strong force moving through the quantum world, carrying colour, reshaping colour, feeling colour, and binding colour into the neutral particles that can exist freely. Every proton in every atom around you contains the work of gluons. Every neutron in every stable nucleus does too. The ordinary world rests on a hidden system of colour charge and gluon exchange, a system so far from common experience that its names sound almost playful, yet so reliable that all chemistry depends on it. The universe does not need its deepest mechanisms to sound serious in order for them to be serious. Sometimes it calls one of its most important messengers a gluon and leaves us to adjust. So as we move further inward, the question becomes less about whether gluons are real and more about what they can do when left to their own rules. They carry the strong force, but they are also touched by it. They connect quarks, but they can also connect to each other. They help make matter stable, but they may also make a particle without ordinary matter at its core. This is where the next step becomes unavoidable. If the messenger can feel its own message, if the carrier of the force is itself charged under that force, then the strong interaction has a strange ability no gentler metaphor can fully contain. The glue can gather, the field cannot, and somewhere in that tiny, restless quantum world, the force carrier may begin holding itself. The strange thing about a gluon is not only that it carries the strong force, the truly unusual part is that it also feels the strong force. That may sound like a small detail, almost like a footnote that wandered into the main text wearing slippers, but it changes the whole story. In many familiar cases, the messenger of a force is not strongly affected by the very force it carries. A photon, for example, carries electromagnetism, but it does not carry ordinary electric charge. This is why beams of light can pass through one another so easily. You can cross two flashlight beams in a dark room and nothing dramatic happens. No little glowing knot forms in the middle. No tiny light traffic officer appears and waves one beam to the left. The photons mostly move along as if the other beam were not there. Gluons are not like that. Gluons carry colour charge, and colour charge is the kind of charge the strong force responds to. So a gluon is not just a messenger passing quietly between quarks. It is more like a messenger who is also part of the message, part of the road, part of the weather, and occasionally part of the crowd. It moves through the strong field while also helping shape that field. It can interact with other gluons, it can influence them and be influenced by them. And because of this, the strong force becomes self-involved in a way that is rare and powerful. The carrier does not simply carry, it participates. This is the little doorway that leads toward the Glueball. If gluons only travelled between quarks and ignored one another, a Glueball would be hard to imagine. There would be no natural way for a group of gluons to hold itself together. They would be like messengers crossing paths in a hallway without stopping to talk. But gluons do talk, in their own quantum way. They pull on one another through the strong interaction. They exchange energy and colour charge. They form tangled patterns in the field. And under the right conditions, the theory says those patterns can become bound states. Not bound states built around quarks, but bound states made from the force carriers themselves. To picture this gently, imagine a small group of people holding a net. If the people are quarks, then the net is the gluon field binding them together. That is the usual picture of the strong force inside particles like protons and neutrons. But now imagine that the net is not passive rope. Imagine the net can grab itself, fold into itself, and hold its own loops together without needing people at the corners. It is a strange image, and perhaps not one to test with actual garden equipment, but it gives a rough feeling for the idea. The force does not merely stretch between matter particles, the force can interact with itself. The glue can cling to glue. Of course, we should be careful with the word cling. Gluons are not sticky in the ordinary sense. They do not have tiny surfaces coated in cosmic syrup. The binding comes from the rules of quantum chromodynamics, the theory of quarks, gluons, and colour charge. But at a human scale, words like cling, knot, and bind are useful stepping stones. They help us cross into a place where the mathematics is exact, but the pictures become cloudy. The strong force is not a physical glue smeared between little balls. It is a field with excitations, charges, symmetries, and allowed combinations. Still, when gluons interact strongly enough, the result can behave like something held together. That something, if it contains no ordinary quark skeleton, is what physicists call a Glueball. The self-interaction of gluons is one of the main reasons the strong force has such a different personality from electromagnetism. With electromagnetism, two electric charges can attract or repel, and the force between them becomes weaker with distance. This matches everyday intuition fairly well. Move a magnet farther from a fridge and it becomes less persuasive. Move a charged object away from another charged object and their effect on each other fades. Gravity behaves similarly in its own long-range way. It weakens with distance, though it never quite stops reaching. The strong force at the scale of quarks does something less familiar. When quarks are pulled apart, the energy in the strong field between them grows. It is not like stretching an ordinary spring forever, because eventually the stored energy can turn into new particles. The universe does not allow lonely colour-charged objects to simply wander off. It responds by making more colour-neutral combinations. This confinement is tied deeply to the self-interaction of gluons. The gluon field does not spread out thinly and politely like the field around an electric charge. It tends to form tight structures between colour-charged particles. Physicists sometimes describe this as a tube of strong field energy between quarks. Again, that is a picture, not a literal hose pipe hidden inside the proton, but it points in the right direction. The the strong field concentrates itself. It resists separation. The gluons, because they interact with one another, help maintain that concentrated field. The result is that quarks remain confined, and colour charge stays hidden inside colour-neutral particles. This is why gluons are so important to the structure of matter. They are not just passing between quarks in a neat, simple exchange. They form an active field whose own interactions help shape the particles we observe. A proton is not three quarks connected by three calm lines. It is a busy quantum system filled with gluon activity. The quarks inside it are surrounded by a sea of interactions, short-lived quark and antiquark pairs, and constantly shifting gluon fields. The gluons carry much of the energy. They help produce much of the proton's mass. They are part of what makes the proton a proton. In a very real sense, most of the substance of ordinary matter comes not from tiny solid pieces, but from the energy of interactions inside particles. That thought is worth letting rest for a moment. The weight of the world around you, the weight of your hand, your pillow, the quiet furniture nearby, is not mainly the weight of little hard beads stacked together. Much of it comes from the energy of the strong force confined inside protons and neutrons. Gluons, though individually not like heavy stones, are central to that energy. They are part of the restless structure that gives matter its mass. So the idea that gluons might form a particle-like object by themselves is not as strange as it first sounds. They already help create mass inside ordinary particles. A glueball would simply be a more direct expression of that capacity, a state where the gluon field gathers without the usual quark framework. There is a useful comparison here, though like all comparisons it eventually starts to wobble. Think of waves on water. A wave is not a separate object made from some special wave substance. It is a pattern in the water. Under the right conditions, waves can interact, reinforce, cancel, or form standing patterns. Now imagine a world where the waves themselves could interact so strongly that a localized pattern persisted for a little while, almost like a thing in its own right. A glueball is not made of water waves, of course, and the quantum strong field is vastly stranger than a pond. But the comparison helps with one idea. A particle can be a stable or temporary pattern in a field. It does not have to be a little pellet of stuff. It can be organized activity. The self-holding nature of gluons also explains why glueballs are not expected to be everyday objects. The conditions needed to create them are extreme. They are not produced by rubbing two balloons together, tapping a spoon on a teacup, or looking suspiciously at a jar of glue. They belong to high-energy particle physics, where collisions can briefly create the energetic conditions needed for the strong field to form unusual states. Even then, if a glueball appears, it will not last long. It will decay into other particles, often into ordinary mesons, leaving behind a pattern that physicists must reconstruct. The glueball is less like a marble you can hold, and more like a chord struck on a piano in a noisy room. The sound is real, but you must listen carefully to separate it from everything else. Why should gluons bind at all if they are massless as force carriers in the theory? This is one of those questions where everyday thinking can lead us into a small ditch. We are used to thinking that mass belongs to objects in a simple way. Something heavy has mass, something light has less mass, something massless should not make a massive bound state. But in quantum field theory, mass can arise from energy and binding. A system made from massless ingredients can still have mass, because the energy of the confined field contributes to the total. The mass of a glueball would not come from heavy gluon building blocks in the ordinary sense. It would come from the energy of the gluon field arranged in a bound state. The strong force does not need little heavy bricks. It can build mass from motion, confinement, and field energy. This is not unique to glueballs. As we have already seen, most of the mass of protons and neutrons comes from the energy of the strong interaction, not from the small masses of the quarks inside. The glueball takes this lesson and makes it cleaner, at least in principle. It says, what if the strong field itself forms the particle? What if the object is not quarks held together by gluons, but gluons held together by gluons? It is a simple sentence, but it contains a very deep rearrangement of intuition. The thing that binds becomes the thing bound. There is another way to approach it. In ordinary life, we tend to think of forces as invisible actions between objects: push, pull, attract, repel, act. The objects are what feel real. The force is what happens between them. But modern physics does not treat fields as secondary decorations. Fields are physical. They carry energy. They can fluctuate. They can be excited. They can have structure. The electromagnetic field can carry energy as light. The strong field can carry energy as gluon activity. When a field becomes organized in a particular way, we may identify that organization as a particle. So when gluons hold themselves, we are not watching a force turn into matter in a magical sense. We are seeing that matter and force are both expressions of fields, and some fields can make particle-like patterns out of their own activity. This is where the Glueball becomes an especially clean test of the strong force. Ordinary hadrons, such as protons, neutrons, and mesons, contain quarks in their main structure. Their behavior tells us about both quarks and gluons together. A Glueball would isolate the gluon side of the story more directly. It would be a particle whose properties arise mainly from the self-interacting gluon field. That makes it scientifically valuable. If physicists can identify a Glueball, they can compare its mass, lifetime, and decay patterns with the predictions of quantum chromodynamics. This would test the theory in the difficult region where confinement dominates. It would also show, in a particularly direct way, that the strong force can generate bound states from its own carriers. The difficulty is that the real world does not always give us pure examples. In a simplified theoretical world containing only gluons, Glueballs are easier to define. Computer simulations of the strong force in such a world predict a whole family of Glueball states. They would differ in properties such as spin and internal quantum behavior, though we do not need to turn those details into bedtime arithmetic. The important point is that the theory does not predict just one possible Glueball. It predicts several possible forms, like different resonant patterns of the gluon field. Some would be lighter, some heavier, some easier to mix with ordinary particles. The lightest predicted Glueball is often expected to have properties that make it resemble certain ordinary mesons, which is both helpful and deeply inconvenient. Helpful because there are real particles to compare with. Inconvenient because resemblance is exactly what makes identification hard. In the actual universe, quarks are present, and they do not politely step aside so gluons can have their photograph taken alone. A Glueball can mix with nearby meson states that have similar properties. The observed particles may then be blends. One might be mostly quark-based with a little gluon content. Another might have a larger Glueball component. Another might be a complicated mixture. This is a little like trying to identify a single flavour in a soup after someone has enthusiastically added 7 kinds of seasoning and then turned down the lights. The flavour may be there, but finding it requires careful comparison, repeated measurements, and a willingness to admit that nature has not labelled the ladle. This mixing does not make Glueballs less real. It simply reflects how quantum systems work. Particles, with the same allowed overall properties, can overlap and combine. Their identity is not always as separate as names suggest. In everyday language, we like clean categories. This is a quark particle. That is a Glueball. This one is ordinary, that one is exotic. Nature often prefers mixtures. A particle detected in an experiment may carry traces of several underlying configurations. The question becomes not simply, is this a Glueball, but how much of this particle's identity comes from gluonic structure? That is a subtler question, and science is often built from subtle questions that look less satisfying on a poster, but are far more honest. When gluons hold themselves, they do so in a world ruled by confinement. That means the Glueball, if formed, must be colour neutral overall. It cannot carry exposed colour charge. It must be arranged so that the colour charges of the gluon field balance in the allowed way. Only then can it exist as a particle state capable of travelling briefly before decay. This is the same general demand placed on ordinary hadrons. The universe does not allow colour charge to appear freely. everything that emerges into the detectable world must be colour neutral. So a glueball is not a clump of exposed strong charge. It is a hidden, balanced arrangement of gluon field energy. The colour is there internally, active and important, but concealed from the outside. The phrase force becomes matter can be a little dramatic if misunderstood, so it is worth keeping it grounded. A glueball would not mean that a familiar everyday push or pull has suddenly hardened into a pebble. It means that the carriers of a fundamental interaction, through their own self-interaction and confinement, can form a bound state with mass and particle-like behaviour. That is already remarkable without needing extra drama. The strong force does not sit outside matter as a separate hand squeezing things together. It is woven into the particles themselves. In a glueball, that woven structure may appear without quarks as the main thread. The self-interaction of gluons also helps explain why the strong force is such a rich source of particles. High-energy collisions can produce many hadronic states, and the strong interaction allows a crowded spectrum of resonances. Some are ordinary mesons, some are baryons, some are more exotic possibilities, including tetraquarks, pentaquarks, hybrids, and glueballs. The particle world at these energies is not a simple cabinet with a few labelled jars. It is more like a lively market where many stalls are open at once, several vendors are shouting similar names, and at least one particle is definitely pretending to be something else. Physicists sort through this by studying patterns, decay channels, production rates, and the quantum properties of each candidate. The glueball is hidden in that crowd, not because it is unimportant, but because it does not necessarily look unique at first glance. There is a calm lesson in this. The deeper we look into matter, the less matter resembles the hard, simple stuff we imagined. Atoms are mostly space in one sense, but not empty in the ordinary sense. Nuclei are dense, but not static. Protons and neutrons are stable, but internally restless. Quarks are confined, gluons self-interact, and the mass of familiar matter arises largely from energy in fields. Then, somewhere in this structure, the possibility of a glueball appears, a reminder that what we call stuff may be a particular way energy behaves when trapped by rules. It is not that the universe is vague. The rules are precise. It is our everyday categories that are a little too blunt. Like trying to cut lace with a bread knife. If you are listening while resting, perhaps with your eyes closed, you might imagine the ordinary world becoming transparent layer by layer. The room remains the room. The blanket remains the blanket. Nothing about daily life needs to be dismissed. But beneath the quiet surface, atoms are held together by electromagnetic interactions, nuclei by the residual strong force, protons and neutrons by quarks and gluons, and inside that deepest familiar layer, gluons are endlessly active. The same activity that binds quarks may, in rare and energetic circumstances, bind itself. That is the idea we are following. Not an object made of glue, but a resonance of the strong field. Not a permanent little bead, but a short-lived pattern of force-carrier self-binding. Not science fiction, but a prediction from the theory that describes the strong interaction. There is something almost practical about the idea once you sit with it long enough. If a gluon carries colour charge, and if colour charge is what the strong force acts upon, then gluons must interact. If they interact, they can form complicated field configurations. If confinement permits colour-neutral bound states, some of those configurations may behave like particles. If those particles exist, they will decay into other hadrons, and if they decay, experiments may be able to detect their traces. The whole chain is difficult, but not unreasonable. It is not a leap over a canyon. It is a series of careful steps through fog, with a lot of expensive equipment waiting on the other side. This self-holding property is what makes gluons unlike the more familiar messengers of light. Photons give us electromagnetic waves, radio, colour, warmth, and the quiet glow of a bedside lamp. Gluons give us the hidden binding that makes atomic nuclei and ordinary matter possible. But because gluons feel their own force, they also give us the possibility of purely gluonic matter. That phrase sounds exotic, and it is, but it is built from the same theory that explains the proton. The Glueball is not outside the standard understanding of particle physics. It is inside it, waiting in one of the hardest corners to verify. And so the force carrier starts holding itself not as a little machine grabbing its own shoelaces, but as a quantum field forming a bound excitation through self-interaction. It is a quiet idea with large consequences. It tells us that forces are not merely influences between things. They can have structure, they can carry energy, they can form states. The strong force, because of the gluon, is especially capable of this. Once that is understood, the Glueball no longer seems like a whimsical name attached to a bizarre fantasy. It seems like the next natural question. If gluons can bind quarks, and gluons can bind other gluons, what would a particle made with no quarks at all really be like? A particle with no quarks at all sounds, at first, like a contradiction. In the familiar story of the subatomic world, the particles inside atomic nuclei are made from quarks, and quarks are held together by gluons. That is the arrangement most of us are gently handed when we first meet modern particle physics. Protons contain quarks, neutrons contain quarks, mesons contain a quark and an antiquark. Gluons do the binding. The quarks are the ingredients, the gluons are the glue, and the particle is the finished little quantum sandwich, though admittedly one that no sensible person would pack for lunch. But a Glueball asks us to loosen that picture. It asks whether the glue itself can form the object. Not quarks held together by gluons, but gluons held together by gluons. No ordinary quark skeleton, no usual matter core, just the strong force, folded into a state that behaves like a particle. This is why Glueballs are so interesting. They sit right at the edge of the way we usually talk about matter. We often say matter is made from particles, and then we list particles as if we are reading ingredients from the back of a cereal box. Electrons, quarks, protons, neutrons. A little more advanced, perhaps, and we add muons, neutrinos, mesons, baryons, and a few other guests who tend to arrive only in particle accelerators or cosmic ray showers. But a Glueball does not fit neatly into the simplest version of that list. It would not be made of the quarks that build protons and neutrons. It would be made from the carriers of the strong force itself. And that means it would be a kind of matter-like object built from what we normally describe as interaction. Now, we should be careful with the phrase matter-like object. A Glueball would not be matter in the everyday sense of something you could scoop into a jar or roll across a table. It would be far too small, far too short-lived, and far too quantum for that. It would not be a tiny ball of sticky stuff, and it would not behave like a bead made of glue. The word ball is doing a lot of friendly but slightly misleading work. In physics, a Glueball would be a bound state of gluons, a compact excitation of the strong field, with definite measurable properties. It would have mass, it would have a lifetime, it would have ways of decaying into other particles. These are the kinds of features that let physicists call something a particle, even when it does not resemble a little solid object at all. The idea becomes easier to accept once we remember that many particles are not simple little lumps of permanent substance. In quantum field theory, a particle is an excitation of a field. The field is the deeper thing. The particle is what appears when that field takes on a certain kind of organized activity. An electron is not a tiny pellet in the old-fashioned sense. A photon is not a speck of shining dust. A gluon is not a microscopic drop of adhesive. These are all excitations of fields, governed by rules that determine how they move, interact, appear and disappear. So a particle with no quarks is not absurd. It simply means that the excitation is not built around quark fields in the usual way. It means the strong field has found a way to make a bound state from its own carriers. Still, there is something wonderfully strange about that. A proton may already be more complicated than the simple picture suggests, but it has quarks as its main identifying ingredients. A neutron does too. A meson is built around a quark and an antiquark. Even many exotic particles that sound far more dramatic than a proton, such as tetraquarks or pentaquarks, still involve quarks. They may involve unusual combinations, extra pairs, or more elaborate internal structures, but quarks remain part of the central story. A Glueball removes them from the central story. It says, for once, let the gluons do everything. Let the force carriers bind themselves into a colour-neutral state. Let the strong interaction create a particle without the usual matter pieces standing in the middle of it. This is why the phrase no quarks at all is so striking. Quarks are deeply tied to our understanding of ordinary nuclear matter. Without quarks, there are no protons and neutrons as we know them. Without protons and neutrons, there are no ordinary atomic nuclei. Without nuclei, there is no chemistry of the kind that makes planets, oceans, bodies, blankets, and half-empty mugs on bedside tables. But Glueballs would belong to another class of possibility. They would not be building blocks of ordinary atoms. They would not sit inside your hand or your pillow as stable ingredients. They would be rare and unstable, produced in energetic processes and quickly decaying. Yet their existence would prove something fundamental about how nature works. It would show that the strong force is not merely an agent acting between pieces of matter. It can create particle states from its own field energy. To see why a Glueball must still be colour neutral, we need to return briefly to colour charge. Gluons carry colour charge, which means they are affected by the strong force. But isolated colour charge is not observed freely in nature. Quarks do not wander around alone. Gluons do not emerge alone. Anything that travels as a detectable particle must have its colour charge balanced internally. Protons and neutrons achieve this balance through combinations of quarks. Mesons do it through a quark and an antiquark. A Glueball would do it through a balanced arrangement of gluons. Inside, the colour structure would be active and complicated. Outside, the particle would appear colour neutral, because that is what confinement demands. The storm is hidden inside the room, and from the hallway the door looks calm. This hidden balance is one reason Glueballs are difficult to picture. If you imagine gluons as little coloured beads, you might be tempted to imagine a Glueball as a cluster of those beads arranged until the colours cancel out. But that picture becomes too mechanical too quickly. Gluons are quantum excitations, and their number inside a bound state is not necessarily fixed like marbles in a pouch. The field can fluctuate. Interactions can create and absorb gluon activity. The Glueball is better thought of as a pattern in the gluon field, a resonance, a self-sustained configuration that exists briefly as a particle state. It is made of gluons in the same broad sense that a wave is made of water, but the wave is not a separate material placed on top of the water. It is water behaving in a particular organised way. A Glueball is the strong field behaving in a particular organised way. This is where the idea of mass becomes important. If a Glueball contains no quarks, where does its mass come from? The answer is not that gluons are little heavy objects packed tightly together. In the theory, gluons are treated as massless carriers of the strong force. Yet a bound state of gluons can still have mass, because mass can arise from energy. A Glueball would contain energy in its confined strong field configuration, and that energy would show up as mass. This is not a special loophole invented for Glueballs. It is already central to ordinary matter. Most of the mass of a proton or neutron comes not from the bare masses of the quarks inside, but from the energy of the strong interaction, including the gluon fields and the motion of the constituents. In other words, the familiar mass of ordinary matter is already telling us that energy in confined fields can become substance in the physical sense. A Glueball would make that lesson almost unmistakably direct. There is something quietly elegant in that. We tend to think of matter as the thing that has mass, and energy as something matter can carry or release. But at the quantum level, the distinction is less like a wall and more like a change in description. A bound system can have mass because of the energy locked into its structure. The mass is not necessarily sitting inside tiny hard pieces. It can be the mass of confinement, motion, field tension, interaction. The Glueball, if identified clearly, would be one of the purest examples of this. A particle without quarks, whose mass comes from the dynamics of the strong force. It would be force energy wearing the outward properties of matter. A helpful way to approach this is to think about music, though only gently, because analogies can become overexcited if left unsupervised. A violin string can vibrate in different modes. The string is the underlying object, and the note is a pattern of motion. You do not ask which little pieces of note are glued together to make the sound. The note is not made from tiny note bricks. It is a vibration with structure. In quantum field theory, particles are not exactly notes, but the comparison helps us avoid thinking too mechanically. A glueball would be like a particular resonant pattern of the gluon field, not a bag of separate things in the ordinary sense, but a field configuration with a recognizable identity. It exists because the rules of the field allow that pattern to form and persist briefly. Different glueballs would correspond to different possible patterns. The theory does not predict only one, it predicts a spectrum, a set of possible gluonic bound states with different properties. Some would be lighter, others heavier. Some would have properties that make them especially likely to mix with ordinary mesons. Others might be more distinct but harder to produce or observe. The lightest possible glueball is often expected to be especially important in experimental searches because lighter states are generally more accessible. But light in this context does not mean light in the everyday sense. It still belongs to the high-energy world of particle physics, where particles appear and vanish in time so short that a blink feels like a geological era. The absence of quarks also affects how glueballs would decay. A glueball would not remain stable. It would quickly transform into other particles allowed by the rules of the strong interaction. Most likely it would decay into mesons. Because mesons are common products in strong processes, this is part of the problem. If a glueball forms and then immediately decays into ordinary mesons, the detector does not receive a little postcard saying, "Greetings, I was a glueball a moment ago." It receives particles flying outward, and scientists must reconstruct what intermediate state produced them. The glueball is inferred from patterns in decay products, from excesses in data, from resonances that appear where theory says they might. It is like trying to identify a guest at a party by looking at footprints, crumbs, and the arrangement of chairs after everyone has left, which is especially difficult if several guests wore the same shoes and all liked biscuits. This difficulty is made worse by mixing. In the real universe, particles with the same overall quantum properties can blend with one another. A pure glueball, in the idealized sense, may not appear as a perfectly pure object. Instead, the gluonic state can mix with quark-based mesons. The particles observed in experiments may each contain some amount of glueball character and some amount of ordinary quark structure. This means the question is not always, which one is the glueball? It may be, which observed particles share the glueball content, and how much of each particle is gluonic. That is less tidy, but it is how nature often behaves. Human labels prefer boxes. Quantum states prefer overlap. This is why a particle with no quarks at all may become, in practice, a particle that is hard to separate from particles with quarks. In theoretical calculations without quarks, glueballs can be clean. In the real world with quarks, the clean object is dressed, mixed, and hidden among neighbours. Imagine baking one plain loaf and several spiced loaves in the same small kitchen, then trying to identify which aroma came from the plain loaf after all the scents have mingled. The plain loaf existed, yes, but the evidence reaches you through a shared atmosphere. Glueballs are something like that, except the kitchen is a particle accelerator and the aroma is a distribution of decay channels, which is admittedly less cosy but more publishable. The possibility of a quarkless particle also changes how we think about the families of particles called hadrons. Hadrons are particles governed by the strong interaction. The familiar hadrons include baryons, such as protons and neutrons, and mesons, made from quark and antiquark pairs. Glueballs would also be hadrons because they are bound by the strong force, but they would be hadrons of a special kind. They would be made from gluonic degrees of freedom rather than valence quarks. This broadens the particle zoo. It tells us that the strong interaction can build more than the simple quark combinations first imagined. It can produce hybrids, where quarks and gluonic excitation both play central roles. It can produce multi-quark states, and it may produce glueballs, where gluons take the lead entirely. The phrase particle zoo is old but useful. As accelerators discovered more and more short-lived particles in the 20th century, the growing list began to look less like a clean table of ingredients and more like a crowded menagerie. Quarks helped bring order to that zoo by explaining many particles as combinations of more basic constituents. But the strong force did not become simple, it became organized in a deeper way. The quark model explained a great deal, yet quantum chromodynamics revealed that gluons are not just invisible strings between quarks, they are dynamic, self-interacting field carriers. Once that is understood, the zoo gains new possible animals. Some are not made from the usual quark pairings, some are bound states of more elaborate structures, and somewhere in those enclosures, difficult to spot because it keeps standing behind the mesons, may be the glueball. It is important not to treat a glueball as a violation of the rules. It is actually a consequence of them. The rules of the strong force allow gluons to interact. The rules of confinement require color-neutral states. The energy of the gluon field can produce mass. Computer simulations of the theory predict glueball states. The challenge is not making the idea fit the theory. The challenge is finding the right experimental evidence in a messy real world. This is often how mature science works. The wild-sounding idea is not wild because it breaks the theory. It is wild because the theory itself, when followed honestly, leads somewhere our everyday imagination would not have gone on its own. This can be a little humbling. The ordinary world teaches us that glue is what holds objects together. It does not teach us that glue can become an object. It teaches us that forces act between things. It does not teach us that fields can form particle states by themselves. But everyday experience is built from a small and stable slice of reality. It is very good at helping us avoid walking into furniture. It is less reliable when we ask what happens inside a proton or in the debris of a high-energy collision. There, nature uses rules that are precise but unfamiliar. A particle with no quarks is not absurd at that scale. It is one of the possible shapes the strong field can take. If a glueball has no quarks, does it count as matter? The answer depends on how strictly we use the word matter. In ordinary speech, matter often means the stuff that makes atoms, and atoms rely on electrons and nuclei made of protons and neutrons. By that standard, glueballs are not ordinary matter. They are not ingredients of stable atoms. But in particle physics, we often use broader categories. A particle with mass, energy, and detectable decay products is physically real whether or not it is part of everyday material stuff. A glueball would not be matter in the kitchen table sense, but it would be a real hadronic state. It would be an object of the strong interaction. It would count as one of nature's possible particles, even if it lives too briefly to build anything familiar. That brief lifetime is not a weakness. Many known particles are short-lived. Some exist only for tiny fractions of a second before decaying, yet their properties can be measured with great care. The universe is full of transient states. A soap bubble may vanish quickly, but no one says it never existed. A note from a bell fades, but it was still a real vibration. A glueball would be far shorter lived than either, but the principle is similar. Physics does not demand that something last a long time to be real. It asks whether the state appears consistently, whether its properties can be measured, whether it fits into the rules, and whether it leaves repeatable traces. In the subatomic world, a brief life can still carry a deep message. The message of a glueball is that the strong force is creative, not creative in the human sense, not sitting thoughtfully with a notebook and a cup of tea, wondering what sort of particle to make next, but creative in the physical sense that its rules allow many structures to emerge. Quarks can be bound into baryons. Quarks and antiquarks can be bound into mesons. Gluons can animate and reshape those structures, and perhaps gluons can form their own bound states. The strong field is not merely an invisible line between ingredients, it is a source of structure in its own right. There is a quiet connection here to the earliest moments of the universe. Shortly after the Big Bang, the universe was hot and dense, filled with a plasma of quarks and gluons before ordinary protons and neutrons settled into place. In such an environment, gluonic fields were not hidden in the same calm way they are inside today's stable matter. The strong force was part of a seething early cosmic state. Glueballs, if they formed in certain conditions as the universe cooled, would have been part of that broader story of how the strong interaction organized itself. We do not need to imagine them floating around today as stable relics in ordinary matter. Their significance is more basic. They help us understand how the force that shapes nuclei behaves when it is allowed to explore its own possibilities. A particle with no quarks also reminds us that classification is a human tool. It helps, but it is not reality itself. We divide particles into groups. We speak of matter particles and force carriers. We draw tables and diagrams. These are extremely useful, and without them physics would be a foggy walk through a warehouse with no labels. But nature is not required to honour our neatest boundaries. Gluons are force carriers, yes, yet they can contribute to mass. They can interact with each other. They may form bound states. So the line between force and matter is not always a wall. Sometimes it is more like a doorway that only opens at very high energies and closes before anyone can take a clear photograph. That is the heart of the Glueball. It is a doorway particle. It invites us to move from the simple idea of matter as assembled pieces toward a richer idea of matter as patterns in fields. It says that a particle can be built not from the familiar quark ingredients, but from the energy of the interaction that usually binds those ingredients. It is not a decorative curiosity. It is a test of our deepest theory of the strong force. If we can identify it, or identify the particles that carry its signature, we learn more about confinement, gluon self-interaction, and the origin of mass in hadronic matter. For now, the cleanest Glueball remains partly theoretical, partly hidden in the data, and partly tangled with ordinary mesons. This is not unusual in frontier physics. Nature often lets us predict something before it gives us a simple way to recognize it. The neutrino was predicted before it was detected. The Higgs boson was expected long before experiments confirmed it. Glueballs have their own kind of difficulty, not because they are necessarily too heavy or too impossible to produce, but because they do not stand alone with an easy signature. They appear in the busiest part of the strong interaction, where many particles share similar properties and decay into similar final states. They are not hidden behind distance, they are hidden behind resemblance, and resemblance is a subtle kind of hiding place. A Glueball may not look entirely unlike a meson. It may decay like a meson. It may mix with mesons. It may appear as one part of a family of particles whose identities overlap. The search therefore requires patience, precision, and a willingness to compare theory and experiment from several directions at once. Physicists look at which particles are produced in gluon-rich processes. They examine decay patterns. They compare masses and internal properties with predictions from simulations. They ask whether a candidate appears where a Glueball should appear, and whether its behaviour is too strange to be explained as a simple quark-based meson. None of this is as dramatic as finding a glowing object in a detector labelled Glueball, but science is rarely that considerate. So when we say a Glueball is a particle with no quarks at all, we are naming the pure idea at the centre of the search. In the real world, the observed states may be mixed. The clean theoretical object may be distributed among several particles, but the concept remains powerful. A Glueball is what happens when the strong field, through gluons, forms a bound state without valence quarks. It is the force carrier becoming part of a particle-like structure. It is the glue holding itself in a colour-neutral bundle of energy. It is not ordinary matter, yet it is physical. It is not stable, yet it can be real. It is not easy to see, yet the theory gives us reasons to keep looking. And this brings us naturally to the difficulty that has followed glueballs for decades. If they are allowed by the theory, and if their existence would teach us so much, why has it been so hard to point to one and say, there it is? The answer lies not in a lack of imagination, and not in a lack of effort, but in the crowded, noisy, deeply entangled world of strong interaction physics. A glueball does not walk into an experiment alone. It arrives wearing the same colours as other particles, leaves through familiar decay routes, and hides its quarkless nature behind a cloud of ordinary hadrons. To understand why seeing one is so hard, we have to follow the trail from creation to decay, from a brief gluonic state to the messy evidence it leaves behind. The frustrating thing about glueballs is that the theory gives us good reasons to expect them, but nature does not seem inclined to hold one up neatly for inspection. If a glueball exists, it does not arrive in a detector wearing a little badge that says, "Hello there, I'm made of gluons and no ordinary quarks. Please record me carefully." That would be helpful, certainly, and physicists would no doubt appreciate the courtesy. Instead, a glueball would be born in a violent high-energy process, live for an unimaginably brief moment, and then decay into other particles that look very much like the particles produced by many less exotic things. By the time the detector sees anything, the original glueball is gone. What remains is a pattern, a spray, a set of tracks and energies, a faint clue buried among many other clues. Particle physics often feels like trying to understand a bird by studying the feathers it left in a storm. To see why this is so difficult, it helps to remember what detectors actually detect. They do not usually see the short-lived particles directly. Many particles in high-energy physics vanish long before they can travel any meaningful distance. Some exist for times so tiny that ordinary words like brief or instant feel far too slow. A detector surrounds the collision point and records the stable or longer-lived particles that come out afterward. Charged particles leave curved tracks, photons deposit energy in calorimeters, other particles create showers or missing energy signatures. From this aftermath, physicists reconstruct the possible chain of events that happened before the detector could notice. It is a little like waking up in the morning, seeing crumbs on the table, a chair slightly moved, and a suspiciously satisfied cat, and then trying to determine whether the biscuit was stolen by the cat, the dog, a visiting raccoon, or yourself at 2 a.m. with no memory of the decision. A glueball makes this detective work especially hard because its decay products are not unique. If it forms, it is expected to decay through the strong interaction into ordinary hadrons, especially mesons. Mesons are particles made from a quark and an antiquark, and they are produced abundantly in high-energy collisions. They are not rare guests at the particle party. They are everywhere, chatting loudly, standing in the hallway, and leaving coats on every available chair. So when a possible glueball decays into mesons, the experimental signal can look like the signal from an ordinary quark-based particle. The final particles may be the same, the energies may overlap. The possible intermediate states may crowd together. The glueball, if it was there, disappears into a sea of familiar outcomes. This is why physicists do not search for glueballs by simply asking whether certain decay products appear. Many things can produce those decay products. Instead, they look for resonances. A resonance is a particle state that appears as a kind of bump or enhancement in the data at a particular mass. When many collision events are collected and analysed, physicists may see that certain combinations of outgoing particles tend to come from an intermediate object with a specific mass and properties. That object existed briefly, then decayed. If the resonance has the right features, it becomes a candidate for some known or predicted particle. But here is the trouble. The strong interaction produces many resonances. Some are ordinary mesons, some may be exotic, some overlap. Some are broad rather than sharp, meaning their signatures are spread out. Looking for a glueball among them is like listening for one soft cello note while an entire orchestra is tuning, and the percussion section has just discovered enthusiasm. The situation becomes even more complicated because glueballs can mix with ordinary mesons. In the cleanest theoretical picture, a glueball is made purely from gluons, with no main quark content. But in the real world, quantum states with the same overall properties can blend together. If a glueball has the same kind of spin and other internal characteristics as nearby quark-based mesons, the physical particles we observe may not be purely one thing or the other. They may be mixtures. One observed particle may be mostly quark-based with a small gluonic component. Another may contain more glueball character. A third may be a different mixture again. This is not nature being messy by accident. It is how quantum systems behave when allowed states overlap. The names we give, glueball or meson, are often cleaner than the physical reality. This mixing is perhaps the greatest practical challenge in the search. A pure glueball may exist in the mathematics, especially in simplified calculations where quarks are left out. But experiments occur in the full universe, where quarks are very much present and not known for stepping politely aside. If the glueball mixes with nearby mesons, there may be no single particle that is simply the glueball. Instead, the glueball identity may be spread across several observed particles. Physicists then have to ask a subtler question. Which of these particles contains the largest gluonic component? Which one behaves most like the predicted glueball? Which decay pattern suggests something beyond an ordinary quark and antiquark state? This is not the clean drama of discovering a new planet. It is more like discovering that several familiar-looking islands are partly made of the same submerged mountain range. The lightest glueball predicted by many theoretical studies is expected to have properties that allow it to mix strongly with certain mesons. This makes it scientifically interesting but experimentally inconvenient. There are several real particles in the mass region where the lightest glueball might appear, and some of them have long been discussed as glueball candidates, or as mixtures containing glueball content. But the evidence is not as simple as one particle matching one prediction. The masses, decay patterns, and production mechanisms all need to be compared. Some candidates appear in processes that should be rich in gluons, which sounds promising. Some decay in ways that seem unusual for ordinary mesons. But none of this is quite the same as a clean fingerprint. It is more like a smudged fingerprint on a very shiny surface, next to several other smudges left by people who were definitely in the room. One reason glue-rich processes are useful is that a glueball, if it is made of gluons, should be more likely to appear in environments where gluons play a strong role. Certain particle decays and high-energy collisions can produce conditions where gluon fields are especially important. Scientists look at these processes carefully, hoping that glueball candidates will be produced more often there than ordinary quark-based states would be. But this is only one piece of the puzzle. Ordinary particles can also appear in glue-rich processes. Quantum chromodynamics is generous in that way, perhaps too generous for anyone hoping for an easy evening. A promising production pattern must be combined with decay information, mass measurements, theoretical calculations, and comparisons across many experiments. There is also the problem of backgrounds. In particle physics, background means all the other processes that can mimic or obscure the signal you care about. The background is not necessarily noise in the simple sense. It is often real physics, just not the particular physics you're trying to isolate. If you are looking for glueballs, ordinary meson production becomes background. Other resonances become background. Combinatorial effects, where unrelated particles are accidentally grouped together in analysis, can become background. Detector limitations can blur the picture. The challenge is not merely to find something interesting, but to prove that the interesting thing is not already explained by something less exotic. That is how science protects itself from wishful thinking. It can be annoying, but it is a useful kind of annoyance, like an alarm clock that saves you from missing a train even though you briefly resent it with your whole soul. Glueball searches also rely heavily on theory, and theory in the strong force can be difficult. Quantum chromodynamics is a beautiful and well-tested theory, but the regime of confinement is hard to solve exactly. For some high-energy processes, the strong force becomes manageable enough for certain calculation methods to work very well. But glueballs belong to the low-energy, strongly coupled world where quarks and gluons are confined. This is the region where simple approximations often fail. To make predictions, physicists use tools such as lattice quantum chromodynamics, where the theory is simulated on a discrete grid using powerful computers. These calculations have provided strong support for the existence of glueballs and estimates of their properties. But connecting those predictions to messy experimental data remains difficult, especially when mixing with quark-based states is included. In a simplified version of the theory without quarks, glueballs are cleaner. The simulations can predict a spectrum of glueball states, and the lightest ones can be identified more clearly. But once real quarks are added, the calculations become more complex. Mixing must be accounted for. Decays become harder to model. The states broaden and overlap. The very thing that makes the real universe real also makes the calculation more demanding. It is rather like practicing a piece of music alone in a quiet room, and then trying to perform it in a crowded station while someone is making announcements about delayed trains. The melody is still there, but good luck hearing every note. Another difficulty is that glueballs are expected to be unstable, and the way they decay can be complicated. If a particle decays through the strong interaction, it often does so quickly and into multiple possible final states. A glueball may decay into pairs of mesons, or into more complicated combinations. Different decay channels carry information about its internal structure. An ordinary quark-based meson may prefer certain decay routes depending on its quark content. A glueball, being gluphonic, might be expected to decay more democratically into different quark flavors, though the real details can be shaped by available energy, mixing, and the dynamics of the strong force. That word democratically is useful only in a loose sense. Nature does not hold a fair election among decay products. It follows probability set by quantum rules, which are usually less concerned with fairness than with allowed interactions. If glueballs were completely pure and did not mix, their decay patterns might stand out more clearly. But because mixing is likely, the decay information becomes harder to interpret. Suppose a particle decays in a way that seems unusual for an ordinary meson. Is that because it contains glueball content? Or because our model of that meson is incomplete? Suppose another particle appears strongly in a gluon-rich process. Is that a sign of a glueball, or can ordinary meson production explain it? Suppose several particles share the expected mass range. Is one of them the glueball, or is the glueball spread among them? These questions do not have quick bedtime answers, though they are very good at keeping graduate students awake. There is also a deeper conceptual challenge. The term glueball can suggest a sharply defined object, but in quantum chromodynamics, especially with real quarks included, the boundary between types of hadrons can become blurry. A meson can contain not only its main quark and antiquark pair, but also gluons and short-lived additional quark pairs as part of its full quantum structure. A glueball can mix with mesons and develop quark components through that mixing. So when we ask whether a particle is a glueball, we may really be asking about the dominant structure of its wave function, though we will avoid the technical phrasing as much as possible and keep the pillows untroubled. The point is that particles are not always made from ingredients in the same simple way a sandwich is made from bread and filling. They are quantum states with overlapping possibilities. The glueball may not be entirely separate from the meson world, even if the underlying pure gluonic state is meaningful. This is why some physicists speak not only of glueballs, but of glueball content. An observed particle may have a certain amount of gluonic character, another may have less. The search becomes a question of composition, but composition in a quantum sense, not a kitchen sense. You cannot slice the particle open and count the gluons. You infer the structure from how it is produced, how it decays, and how well it matches theoretical expectations. It is careful, statistical, indirect work. The evidence builds not from one dramatic photograph, but from many lines of reasoning leaning in the same direction. The history of particle physics has many examples of particles discovered through indirect evidence, so this is not unusual. The neutrino was inferred before it was detected. Quarks themselves were accepted through patterns and scattering evidence before anyone imagined seeing a free quark, which confinement then told us we would not see anyway. The Higgs boson was found through its decay products, not by someone watching a little Higgs drift across a screen. Short-lived particles are routinely known through what they become. Glueballs are difficult not because indirect detection is impossible, but because the indirect signs are so entangled with ordinary strong interaction physics. The detectors used in modern experiments are extraordinary instruments. They can record enormous numbers of events, measure particle energies and directions, and help reconstruct decays with impressive precision. But even the best detector cannot remove the fundamental fact that glueballs decay into common hadrons and mix with other states. More data helps, better analysis helps, improved theory helps. But the glueball remains shy because its signature is not simple. It hides in plain sight, among particles that may look similar enough to be relatives, neighbours, or very convincing imposters. This is also why different experiments and theoretical groups can interpret the situation differently. One analysis may favour a particular particle as having strong glueball character. Another may distribute the glueball content among several particles. A model may handle mixing one way, while another model emphasises different decay data. This does not mean scientists are simply guessing. It means the problem is genuinely complex and the evidence must be weighed carefully. Science often advances through this kind of slow narrowing, where uncertainty is reduced step by step rather than swept away in one grand gesture. The universe does not always provide a trumpet fanfare. Sometimes it provides a slightly uneven graph and asks everyone to be patient. There is a gentle irony here. Glueballs are difficult to see because gluons are so effective at what they do. The same confinement that makes the strong force strong, the same self-interaction that allows gluons to bind, also prevents gluons and glueballs from appearing in simple isolated ways. The properties that make glueballs possible also make them hard to identify. If gluons did not interact with themselves, glueballs would not exist. But because gluons interact strongly and are confined, any glueball that forms is quickly absorbed into the busy world of hadrons. Nature gives with one hand and hides the receipt with the other. It may help to imagine trying to study a whirlpool in a fast-moving river. The whirlpool is real. It has structure. It may last for a while and then dissolve. But if the river is full of other eddies, waves, splashes, and floating leaves, identifying one particular whirlpool after it has vanished is not straightforward. A glueball is somewhat like that, except the river is the strong field, the whirlpool is a gluonic-bound state, and the floating leaves are mesons, which is probably not a comparison the mesons would appreciate. The important point is that the glueball is not absent simply because it is hard to isolate. A transient pattern can be real even when the surrounding medium makes it difficult to pick out. The difficulty is also connected to scale. Glueballs are expected at energy scales where strong interaction physics produces many hadronic states. If they were much lighter and had a clean rare decay mode, perhaps they would have been easier to find. If they were stable, they would be easier still, though that would raise other questions. But expected glueball candidates live in the crowded middle, where ordinary meson spectroscopy is already complicated. Spectroscopy in this context means the study of particle states and their properties, not little rainbows through a prism, though the spirit is similar. Physicists are sorting the spectrum of possible hadrons, trying to understand which patterns belong to which underlying structures. Glueballs are one colour in that spectrum, but not one that separates cleanly under ordinary light. Another reason the search is challenging is that strong force particles often have broad widths. In simple terms, a very short-lived particle may correspond to a less sharply defined mass in the data. Instead of a narrow spike, it may appear as a broad bump. Broad bumps are harder to interpret, especially when several of them overlap. This is not because the particle is sloppy, though it is tempting to accuse it of poor presentation. It is a consequence of the relationship between lifetime and energy uncertainty in quantum physics. We do not need equations to feel the effect. A brief, unstable state does not leave the same crisp signature as a longer-lived one. Glueball candidates may therefore appear as features that require careful modelling rather than obvious peaks. Then there is the matter of decay channels that involve neutral particles. Some decay products are easier to detect than others. Charged particles leave tracks. Neutral particles may require different detector systems or reconstruction methods. Some final states include particles that themselves decay quickly, adding more layers to the reconstruction. The more complex the final state, the more opportunities there are for uncertainty, background, and misidentification. A glueball could decay through several routes, and understanding the whole pattern may require combining data from multiple experiments. It is like trying to assemble a jigsaw puzzle from pieces found in different rooms, while several pieces from other puzzles have also been helpfully added by someone with a very relaxed attitude toward organisation. Despite all this, the search is not hopeless. Quite the opposite. The difficulty is part of what makes glueballs valuable. A clear identification would mean that theory, computation, and experiment have all converged on one of the most subtle predictions of the strong force. It would deepen our confidence in quantum chromodynamics in the confinement regime. It would show that gluon self-interaction is not merely a feature of the equations, but a structure-forming reality in the particle spectrum. It would give physicists a new handle on the way mass emerges from strong field energy. And it would help clarify the complicated family of hadrons that appear in experiments. One might ask why we should care about a particle that is short-lived, hard to detect, and not part of ordinary matter. That is a fair question, especially late at night when many practical things already seem demanding enough. The answer is that glueballs probe the rules behind ordinary matter. They are not important because they build your chair directly. They are important because the same force that may form glueballs also holds together the protons and neutrons in every atom of that chair. Studying the exotic behaviour of the strong force helps us understand its ordinary work. The unusual case reveals the general rule. Sometimes the best way to understand a familiar machine is to see what it does under unusual conditions, preferably without standing too close to the machinery. There is also a philosophical charm to the search, though we should keep our feet on the ground. Glueballs challenge the simple separation between matter and force. They show that the carriers of an interaction may form particle states themselves. If confirmed clearly, they would be among the most direct examples of a force field becoming a matter-like object through its own dynamics. That is not merely a curiosity, it is a clue about the kind of universe we live in, one where fields are primary, particles are excitations, and the things we call objects are often stable patterns in deeper activity. The glueball is difficult to see because it belongs to that deeper level, where the categories are real but not simple. The hunt for glueballs has therefore become a careful balancing act. Physicists do not want to declare victory too soon, because many ordinary explanations can mimic parts of the signal, but they also do not want to ignore the evidence that certain observed particles may contain significant gluonic content. The likely truth may be less tidy than a single discovery announcement. It may be that glueball content is shared among several resonances. It may be that improved data and better calculations gradually reveal which states are most gluonic. It may be that future experiments identify cleaner signatures or clarify old puzzles. In science, especially in the strong interaction, answers can arrive not as a light switching on, but as a fog slowly thinning. And that, in a way, suits the glueball. It is not a loud particle. It is a hidden pattern of the hidden force. It emerges from the part of physics that makes ordinary matter possible, but rarely shows itself directly. It decays before it can be held, mixes before it can be named, and leaves behind only the traces allowed by the strong interaction. To find it, physicists must follow those traces through crowded data, difficult theory, and many possible lookalikes. The task is demanding, but the reward is a clearer view of how the strong force organises energy into particles. So when we say glueballs are difficult to see, we do not mean they are small in the simple sense, though they certainly are. We mean they are hidden by the very rules that create them. They are born in strong fields, decay into ordinary hadrons, mix with nearby mesons, and appear only through statistical patterns in complex experiments. They are not invisible because they are unimportant. They are invisible because they live where nature is most tightly woven. And to understand where they may hide, we have to move into that dense and restless environment where quarks and gluons no longer behave like separate little things, but like a hot, shifting quantum soup from which the familiar particles of the universe can emerge. To understand where glueballs may be hiding, we need to enter a place that is not really a place in the ordinary sense. It is not a cave, not a cloud, not a tiny warehouse inside the proton with shelves marked quarks, gluons, and miscellaneous quantum clutter. It is the restless environment created by the strong force itself, the dense, shifting world where quarks and gluons behave less like neat individual objects and more like ingredients in a hot active soup. Physicists often use the phrase quantum soup for this kind of situation, and for once the kitchen metaphor is not too bad, provided we do not take it too literally and start wondering whether the universe owns a ladle. In the strong interaction, especially under extreme conditions, quarks and gluons can move through a shared medium, collide, exchange energy, and then cool or reorganize into the particles we eventually detect. Somewhere in that process, if the conditions are right, the gluon field may briefly form the kind of self-bound structure we call a glueball. The word soup is helpful because it reminds us that the strong force is not always best pictured as a few tiny objects connected by simple lines. Inside ordinary protons and neutrons, the quarks and gluons are already in constant motion. In high-energy collisions or in the early universe, the situation becomes even more active. The energy density rises, the fields fluctuate intensely. Quarks and gluons can become less confined in the usual hadronic packages for a short time, forming a state where they move through a hot medium before eventually recombining into ordinary particles. This state is often called quark-gluon plasma. It is one of the most extreme forms of matter known, and it is not plasma in the everyday glowing gas sense used for neon signs or certain dramatic desk lamps. It is a state where the usual boundaries between hadrons have melted, at least briefly, and the ingredients of hadrons are moving in a collective, strongly interacting environment. Now, this does not mean quarks and gluons become simple little free marbles floating peacefully in a bowl. The strong force is still strong, the medium is not calm. It behaves more like an almost perfect fluid, with intense interactions and rapid changes. In heavy ion collisions, where large atomic nuclei are smashed together at extremely high energies, physicists create tiny droplets of this quark-gluon plasma for incredibly short times. These droplets expand and cool almost immediately, and as they cool, quarks and gluons become confined again into hadrons. The final result is a storm of particles flying into detectors. From those final particles, scientists reconstruct what the plasma was like and what may have formed during the transition back into the familiar world of hadrons. It is a bit like trying to understand the texture of a soup by analysing the steam after someone has already spilled the bowl, which is not ideal, but particle physics has learned to work with difficult dinner situations. This hot, dense medium is interesting for glueballs because glueballs are made from gluon dynamics. If there is ever a place where gluons are abundant, active, and interacting strongly, a quark-gluon plasma seems like a natural place to look for signs of gluonic-bound states. But the situation is not as simple as saying more gluons means more glueballs. The plasma is extremely hot, and bound states can be difficult to form or survive at high temperature. A glueball needs the gluon field to arrange itself into a color-neutral, particle-like configuration. In a very hot medium, such a structure might be disrupted before it can become recognizable. As the medium cools, however, the strong force begins locking quarks and gluons back into hadrons. This process, called hadronization, is where many possible states can form. Glueballs, if they are produced, may appear during or after this cooling transition, hidden among the large number of ordinary particles created at the same time. Hadronization is one of those words that sounds as if it should come with a clipboard and a safety warning. It simply means the process by which quarks and gluons turn into hadrons, the colour-neutral particles that can exist freely. When high-energy collisions produce energetic quarks and gluons, those colour-charged objects cannot remain exposed. The strong force reorganises the energy into allowed combinations, creating showers of mesons, baryons, and other hadronic states. This is the moment where the invisible rules of confinement become visible through their results. You never see the free quark strolling away. You see the hadrons that form because the quark could not stroll away. If glueballs are part of the possible hadron family, then hadronization is one of the processes where they may be born. The difficulty is that hadronization produces many things at once. It is not a quiet workshop where one particle is assembled at a time and placed gently on a velvet tray. It is a rapid, crowded transformation of energy into a whole spray of allowed particles. Ordinary mesons are produced in great numbers, baryons appear, resonances form and decay, particles interact with one another before reaching the detector. In heavy ion collisions, the environment is especially crowded because the number of produced particles can be enormous. Somewhere in that crowd, a glueball may form and decay, but its trace must be separated from the many ordinary processes happening at the same time. It is like trying to hear a single whispered recipe in a busy kitchen where every pot is boiling, every timer is ringing, and someone has just dropped a spoon. There are also other gluon-rich places where glueballs might hide. Certain decays of heavy particles can produce final states with lots of gluon activity. High-energy collisions involving protons can create gluon jets, sprays of particles that originate from energetic gluons. Some processes are especially useful because they are expected to favour the production of particles with strong gluonic content. Physicists pay attention to these environments because a glueball should, in principle, be more comfortable being born where gluons are already doing much of the work. But again, comfort is relative. Ordinary mesons can also be produced there. A gluon-rich process does not guarantee a glueball. It merely raises the chance that if glueballs exist, their fingerprints may be more visible against the background. A useful example is a kind of particle decay, where a heavy quark and its antiquark annihilate and produce gluons, which then turn into hadrons. Since gluons are central in the intermediate stage, these decays have long been considered promising places to look for glueball candidates. The reasoning is straightforward enough. If a particle is made mainly from gluons, then a process rich in gluons may produce it more readily than a process dominated by other mechanisms. But the final evidence still comes from decay products. The possible glueball appears as a resonance among other resonances. Its properties must be reconstructed, compared, and tested against alternatives. The soup may be rich in the right ingredients, but the finished dish still has to be identified after it has been served in pieces. Inside this quantum soup, gluons are not passive background material. They are active, self-interacting components of the strong field. This matters because a glueball is not just a random clump of particles, it is a bound state allowed by the self-interaction of gluons. In a hot or energetic environment, the gluon field can fluctuate strongly. Sometimes those fluctuations may settle briefly into configurations with the right properties. If the configuration is color neutral and has enough coherence to behave like a particle state, it can be thought of as a glueball candidate. But the word briefly is doing a great deal of work here. These states, if formed, are unstable. They decay almost immediately into more familiar hadrons. The detector sees the final hadrons, not the gluonic structure that preceded them. This is why physicists often speak in terms of resonances. A resonance is a temporary state that forms and decays, leaving a pattern in the distribution of final particles. In a messy hadronic environment, resonances can overlap. Some are narrow and easier to identify. Others are broad, spread out across a range of possible energies, making them harder to separate from background. Glueballs, especially the lighter ones expected in the strong interaction, may appear as broad or mixed resonances. They may not produce a sharp, lonely peak that stands up in the data and waves politely. They may appear as part of a complicated landscape of enhancements, dips, and interference patterns. If that sounds less satisfying than discovering a new planet through a telescope, it is. But it is also how much of subatomic reality reveals itself. The quantum soup is not only found in modern accelerators, it also belongs to the history of the universe. In the earliest moments after the Big Bang, the universe was far hotter and denser than it is now. Before ordinary protons and neutrons formed, matter existed in a state where quarks and gluons were not confined into the familiar hadrons we know today. As the universe expanded and cooled, the strong force gathered quarks and gluons into color-neutral particles. This cosmic hadronization was one of the great settling processes in the early universe. If glueballs can form during transitions from gluon-rich states into hadrons, then the early universe may have briefly contained glueball-like states as well. They would not have survived as stable objects in ordinary matter, but they could have been part of the strong force story as the universe changed from a hot quantum medium into a world capable of atoms. There is something grounding about this. Glueballs are not just exotic curiosities that might appear in machines built by clever humans. They are connected to the same conditions nature itself once explored at cosmic scale. Particle accelerators, in this sense, do not create unnatural physics so much as recreate small controlled hints of conditions that the universe once knew very well. When heavy nuclei collide and form quark-gluon plasma, the droplet is tiny and short-lived, but it lets physicists study the behavior of the strong force under conditions closer to those of the early universe than anything found in ordinary matter today. If glueballs hide in such transitions, then finding them would tell us not only about particles, but about how the universe learned to make the familiar hadrons from its early hot state. The challenge is that the early universe did not leave us a neat archive of individual glueballs. If they formed, they decayed long ago. We cannot look back and photograph one. Instead, we study the theory, simulate the strong force, and create high-energy environments where similar processes may occur. This is one reason glueball physics sits at a crossroads between theory, computation, and experiment. The theory says gluonic-bound states should exist. Computation helps estimate their properties. Experiments search through particle data for matching states. None of these approaches is enough alone. The theory without experiments is a map of a country not yet visited. The experiments without theory are a crowded room of clues with no organizing story. The computations are the bridge, but even bridges require careful maintenance and occasionally a lot of patience. Lattice simulations are especially important here. Since the strong force becomes difficult to calculate directly when confinement dominates, physicists simulate quantum chromodynamics on a grid. These simulations allow them to study how gluon fields behave and what kinds of bound states should appear. In versions of the calculation where quarks are removed, glueballs emerge clearly. This is a strong theoretical sign that the pure gluon field can form particles. Adding quarks makes the situation more realistic and more complicated. The glueball states can mix with quark-based mesons, and the clean theoretical picture becomes less distinct. But the underlying message remains. The strong field has the capacity to make gluonic-bound states. The quantum soup contains the right kind of physics. When the soup cools into ordinary hadrons, identity becomes difficult. A state that began as mostly gluonic may mix with nearby meson states. By the time it decays into final particles, its origin is partly disguised. This is why some observed scalar mesons have been considered possible carriers of glueball content. They are not necessarily pure glueballs, and that is the key point. The real world may distribute the pure gluonic state across several physical particles. In this view, the glueball is not hiding as one perfectly isolated particle, but as a component inside a small family of resonances. That is a subtle kind of hiding. Not invisible exactly, blended, like a quiet flavour spread through several spoonfuls rather than sitting in one obvious lump at the bottom of the bowl. This blending is not a failure of the idea. It is a natural outcome of quantum mechanics. If two states have the same external properties, they can mix. A quark-based meson and a glueball with similar allowed characteristics do not have to remain separate. The physical particles detected in experiments can be combinations. This means that the phrase "a particle with no quarks at all" describes the ideal gluonic state, while the observed candidates may be mixed states. The pure glueball may be a starting point in the theory, but the real particles may carry both gluonic and quark content. Again, the universe is not confused, it is just not organising itself according to the simplest labels in our notebooks. In the quantum soup, even the vacuum is not simple. The vacuum of quantum field theory is not empty in the everyday sense. It has structure, it allows fluctuations, it influences the behaviour of particles and fields. For the strong force, the vacuum is especially rich. It is tied to confinement, to the formation of quark and gluon condensates, and to the mass structure of hadrons. We do not need to wander too far into those technical forests tonight, but it is worth knowing that what physicists call empty space is not a blank stage. The strong interaction vacuum has properties that help determine what kinds of particles can exist. Glueballs are part of that story because they represent excitations of the gluon field itself. They are not added on top of the strong vacuum like decorations. They arise from the same field dynamics that give the vacuum its complex character. This can feel strange because we're used to thinking of soup as something contained in a bowl. But the quantum soup of the strong interaction is not a literal substance sitting somewhere. It is a way of describing the active field environment under certain conditions. In a proton, the soup is confined within a small stable hadron. In a quick gluon plasma, it becomes a hot medium created briefly in extreme collisions. In the vacuum, the fields still have underlying structure. Across these different contexts, gluons are never simply quiet. They interact, fluctuate, bind, and reshape the particle world. A glueball may hide wherever gluonic dynamics are strong enough and organised enough to form a temporary colour neutral state. Experimental searchers therefore look across several kinds of environments. They examine decays that produce gluons. They study collisions where gluon-rich states may form. They analyse hadron spectra, looking for resonances that do not fit neatly into ordinary quark models. They compare how often certain particles are produced in different settings. They examine decay patterns into various mesons. If a candidate is produced strongly in gluon-rich processes, if it has a mass near theoretical expectations, if its decay behaviour is unusual for a simple quark meson, and if it fits into a broader mixing picture, then it becomes more interesting. No single clue is enough. The case must be built from many clues, like assembling a sleepy but determined courtroom argument, where the witness is a particle that vanished before the trial began. The word hide is important. Glueballs may hide not because they are rare in every possible environment, but because they decay into common particles. They may hide because they mix. They may hide because their signatures overlap with other resonances. They may hide because the strong force produces complicated backgrounds. And they may hide because our theoretical tools, though powerful, still have limits in the very regime where glueballs live. This is a different kind of invisibility from being too far away or too faint. It is invisibility by resemblance, by transformation, by participation in a crowded system. The glueball does not stand outside the strong interaction waiting to be noticed. It is made from the strong interaction, and then it dissolves back into the strong interaction's ordinary products. There is a nice lesson here about how science often finds hidden things. The hidden thing is not always behind a wall. Sometimes it is woven into the pattern in front of us. To see it, we must learn what the pattern would look like without it, what it would look like with it, and where the difference might appear. Glueballs require that kind of seeing. Physicists compare models of ordinary mesons with data. They ask where extra states appear. They test whether the number of observed particles exceeds what the simple quark model predicts. They ask whether certain resonances appear too strongly in gluon-rich processes. They look for consistency across experiments. The Glueball is not a single clue. It is the explanation that may make several clues fit together. This is why the quantum soup is such an appropriate hiding place. It is dense with possibility. It contains quarks, gluons, fields, fluctuations, bound states, decays, and mixtures. It is where the clean categories of the particle table become active processes. A quark is not just listed, it interacts. A gluon is not just named, it binds. A meson is not merely an entry, it can mix. A Glueball is not simply absent or present. It may be a component, a resonance, a temporary organization of the field. This is not less real than a simple particle picture. It is more realistic. The universe is under no obligation to be easy to sort. Still, there is something calming in the fact that even this complicated soup follows rules. It is not chaos in the careless sense. The strong interaction is governed by quantum chromodynamics. Conservation laws apply. Color neutrality matters. Allowed decays follow probabilities. Resonances have properties. Detectors record measurable outcomes. The complexity is not disorder without meaning. It is order at a level too rich for simple pictures. That is often how modern physics feels. Not vague, but deep. Not random, but layered. Like a quiet room that seems simple until you learn how many atoms, fields, and interactions are making its stillness possible. As we move through this part of the story, the Glueball becomes less like a single object hiding under a blanket, and more like a pattern that may appear briefly during the reorganization of strong fields. The quantum soup is where gluons are active enough to form such patterns, and where those patterns are complicated enough to disguise themselves. It is where force and matter are not separate categories, but interacting descriptions of the same underlying fields. It is where a self-bound gluon state can be born, mix, decay, and leave behind only a trace in the hadronic crowd. And because the trace is subtle, the hunt must be careful. The next step is to follow how physicists actually search for that trace, which experiments give them hope, which candidates have drawn attention, and why the first clear Glueball, if it's finally pinned down, will not look like a tiny glowing ball of glue at all, but like a pattern in data that quietly says the strong force has made a particle from itself. The hunt for the first real Glueball has been going on for a surprisingly long time, and like many long hunts in physics, it has not looked much like a dramatic chase. There has been no single glowing object caught in a net, no particle calmly stepping out of a detector and introducing itself with perfect manners. Instead, the search has unfolded through decades of careful measurements, competing interpretations, promising candidates, disappointing disappearances, and patient arguments about what the strong force is really showing us. A Glueball, after all, is not expected to be polite. It is expected to form briefly, decay quickly, mix with ordinary particles, and leave behind a trace that looks annoyingly similar to several other traces. If nature wanted to make this easy, it could have chosen a less crowded hiding place than the middle of strong interaction physics. But nature, as we have learned, enjoys placing the most interesting things in the least convenient drawers. The reason physicists keep looking is that Glueballs are not just speculative decoration. They arise naturally from the theory of the strong force. If gluons carry color charge, and if gluons interact with other gluons, then the strong field should be able to form bound states of its own. The idea is built into the deep structure of quantum chromodynamics. In simplified calculations, especially those that study the pure gluon field without the full complication of quarks, Glueballs appear quite clearly. They are predicted as a family of possible particles, each one a different allowed pattern of the gluon field. The lightest one in many calculations is expected to be a scalar glueball, which means it has no spin in the relevant sense, and behaves as one of the simplest possible gluonic bound states. But the moment we return from the clean world of calculation to the actual universe, quarks come back into the room, sit down heavily, and make everything more complicated. The earlier searches grew out of a broader attempt to understand the crowded family of hadrons. Hadrons are particles shaped by the strong interaction, and for much of the 20th century physicists discovered more and more of them. Some fit nicely into the quark model, others looked unusual. As the strong force theory matured, researchers began asking whether some of the extra states might not be ordinary quark combinations at all. Maybe some were hybrids, with quarks and an excited gluon field. Maybe some were multi-quark states, and maybe some were glueballs. This was an appealing possibility because the particle spectrum seemed to contain more resonances than the simplest models could easily organize. When the shelves are crowded, one begins to wonder whether someone has been storing extra boxes behind the obvious ones. One of the classic hunting grounds has been radiative decays of a particle called JPSI. We can say the name gently, like a small code word from the particle world. JPSI is made from a charm quark and its antiquark, and when it decays in certain ways it can produce a photon along with gluons. That matters because gluons are the raw material, so to speak, of a glueball. If a decay creates a gluon-rich environment, then it may be a good place for gluonic states to form. This does not mean every interesting particle produced there is a glueball, of course. That would be much too convenient, but it does mean that radiative JPSI decays have been especially important in the search. They are like a pond where the kind of fish you want might plausibly live, even if the pond is also full of reeds, shadows, and several fish that look suspiciously similar from a distance. Another clue comes from how a candidate particle behaves in photon-photon collisions. Ordinary quark-based mesons can often couple to photons because quarks carry electric charge. A pure glueball, made mainly from gluons, should not couple to photons as strongly. So if a particle is produced strongly in gluon-rich processes but weakly in photon-based processes, physicists become interested. Not convinced, but interested. In this field, interested is already a respectable achievement. It means the particle has survived the first round of skeptical glances. It means someone may put it on a slide at a conference, and perhaps cause several people near the front to lean forward slightly. For many years, two of the most discussed scalar glueball candidates were particles known in spoken form as F0 1500 and F0 1710. Their names are not cosy, but particle names often have the warmth of filing cabinet labels. These particles live in the mass region where the lightest scalar glueball has often been expected. Both have properties that made physicists wonder whether one of them, or perhaps both in different ways, might contain significant glueball character. The debate has lasted because neither candidate offers a perfect answer. One may fit certain production or decay clues, another may fit theoretical expectations more naturally. Some models distribute the glueball content among several nearby particles, rather than placing it all in one. This is the sort of situation where nature seems to say, yes, you are looking in the right neighbourhood, but no, I will not tell you which house. The F0 1500 attracted attention because it did not fit simply into some quark model expectations, and because its decay pattern seemed unusual. The F0 1710 became especially interesting because some theoretical and experimental arguments suggested it might have a large gluonic component. In particular, its production in gluon-rich environments and its relationship to lattice calculations helped make it one of the leading scalar glueball candidates. But the important word is candidate, not confirmed visitor, not settled resident. Candidate. The distinction matters. Physics is careful with such words because history is full of promising hints that later changed shape under better data. A particle can look exotic from one angle and ordinary from another, rather like a household cat that appears mystical in moonlight and then knocks over a plant at breakfast. The difficulty with the scalar candidates is mixing. Imagine the pure Glueball predicted in a simplified gluon-only world. Now place it in the real world, where ordinary quark and antiquark mesons exist with similar properties and similar masses. These states do not have to remain separate. Quantum mechanics allows them to mix. The observed particles can become blends of gluonic and quark-based structures, so the hunt may not lead to one pure scalar Glueball standing alone. It may lead to a set of scalar mesons, each carrying some fraction of Glueball identity. This possibility is less tidy than a single discovery, but it may be closer to the truth. It is not a failure if the Glueball is mixed. It is a reminder that particles are quantum states, not labelled beads in a drawer. This is why physicists use many clues at once. They study masses, they study decay patterns, they study production rates in different kinds of experiments. They look at whether a candidate appears in processes rich in gluons. They check whether it is suppressed in processes where ordinary electrically charged quark structure might be expected to appear more clearly. They compare the number of observed particles with the number predicted by quark models. They analyse how strongly different resonances overlap. No single clue can carry the whole case. A Glueball search is not a yes or no question asked of one plot. It is a slow accumulation of evidence, like trying to identify a song by hearing fragments of melody through several walls while the kettle is also boiling. Modern experiments have brought enormous improvements. Detectors can gather vast samples of particle decays and reconstruct final states with impressive precision. One of the most important experiments in this story is BES3 in Beijing, which has collected very large numbers of JPSI decays. This matters because rare processes become easier to study when the number of starting events is huge. If you're looking for something that appears only occasionally, you need patience, good instruments, and a truly unreasonable amount of data. Particle physicists are quite good at all three, though the patience may occasionally be assisted by coffee. BES3 has played a major role in renewing interest in Glueballs, especially through studies of a particle often called X2370. This candidate is not the same kind as the lightest scalar Glueball. It is discussed as a pseudoscalar Glueball candidate, meaning it belongs to a different category of quantum properties. The name sounds technical because it is, but the essential idea is simple enough. The strong force theory predicts not just one possible Glueball, but a spectrum of them. Some would have different internal properties from the lightest scalar state. X2370 became interesting because it appears in gluon-rich radiative JP-psi decays, and recent studies have measured properties that are consistent with expectations for a pseudoscalar Glueball. That does not make the case closed, but it does make the search feel very much alive. The word Glueball-like is often used for X2370, and that caution is important. It means the particle has features that fit the Glueball idea, but physicists are still careful about calling it the first confirmed Glueball without qualification. This careful language may sound less exciting than a headline, announcing that the first Glueball has finally been found. But in science, caution is not lack of wonder, lack of. It is how wonder survives contact with evidence. A Glueball-like particle is already fascinating. It says the data are pointing toward gluonic behaviour. It says the theory and experiment may be coming together. It says the strong force may be showing us one of its long-hidden tricks. But it also leaves room for alternative interpretations, improved measurements, and the possibility that the final story is more mixed than the simple one. The hunt is also shaped by partial wave analysis, which is one of those phrases that sounds like it might belong to either particle physics or someone trying to sleep at the beach. In this context, it means a detailed method for disentangling overlapping particle contributions in a decay. When several resonances can lead to the same final particles, the observed data contain interference among different possibilities. Partial wave analysis helps determine which intermediate states are present and what their properties are. It is a powerful tool, but also a delicate one. The results depend on careful modelling and high-quality data. For Glueball candidates, where the signatures are already subtle, such analysis is essential. Without it, the particle crowd becomes too noisy to understand. One of the reasons BES3 has been so important is that it can study radiative J-psi decays with enormous statistical samples and relatively clean conditions for certain channels. That lets physicists measure masses, decay modes, and internal properties more precisely than before. When the properties of X2370 were measured in more detail, they strengthened the argument that it may be connected to a pseudoscalar Glueball. New decay modes have also been observed, giving more pieces of the puzzle. Each new channel is like another window into the particle's identity. If all windows show the same strange room, confidence grows. If one window shows a completely different room with a llama in it, confidence pauses for a meeting. Still, even a strong candidate must be handled carefully. A particle can be produced in a gluon-rich process and still not be a pure Glueball. It might be an ordinary meson with unusual properties. It might be a mixture. It might belong to a more complicated structure. The strong interaction has many ways to surprise us without necessarily giving us exactly the object we hoped for. This is why researchers compare observations with lattice quantum chromodynamics, phenomenological models, and results from other experiments. A true Glueball identification needs consistency across many tests. It is not enough for a particle to have the right mass. It needs the right pattern of production, the right decay behavior, the right quantum properties, and a convincing explanation of why ordinary alternatives are less successful. The scalar Glueball search and the pseudoscalar Glueball search are related but not identical. The scalar case has long been central, because the lightest Glueball predicted in many calculations is scalar. The pseudoscalar case has become especially exciting because of recent experimental progress with X2370. Together, they show that the hunt for Glueballs is not one straight road. It is more like a network of paths through the strong force landscape. One path leads through scalar mesons around the region of F0 1500 and F0 1710. Another leads through heavier pseudoscalar candidates like X2370. Other paths may involve tensor candidates, hybrid states, or future experiments that produce gluon-rich environments in different ways. The forest is large, and the Glueball may have left more than one trail. There have also been past candidates that rose and faded. This is normal in particle physics. An early signal may look promising, then later data may fail to confirm it or may show that it fits a different interpretation. Some particles once discussed as Glueball candidates are no longer favoured. Others remain under debate. The history can feel untidy, but it is actually part of the scientific process working properly. Ideas are tested, candidates are compared, better instruments arrive, old claims are revisited, the story sharpens. A failed candidate is not wasted effort. It tells physicists what the Glueball is probably not, which is useful, if slightly less glamorous than discovering what it is. In this sense, the hunt for the first real Glueball resembles the search for a face in a fogged mirror. At first, many shapes look suggestive. With better light, some vanish, others remain, a few become clearer, but the mirror is never fully clean because the strong force itself creates the fog. Confinement hides free gluons, mixing blurs identities. Decays replace original states with final particles. Backgrounds imitate signals. The evidence must be read through layers. If the first confirmed Glueball is finally accepted, it may not come as a sudden shout, but as a gradual agreement that one interpretation has become far more convincing than the rest. Science sometimes discovers things not with a bang, but with a committee becoming cautiously less annoyed. The phrase first real Glueball is also tricky, because reality in particle physics is not always tied to purity. Suppose an observed particle is 70% gluonic in character and 30% quark-based. Is it a Glueball? Some physicists might say it has strong Glueball content. Others might reserve the word Glueball for a more idealized state. If several particles share the content of an underlying Glueball, which one gets the title? These are not merely naming problems. They reflect the way quantum states mix. The first real glueball may not be a perfectly pure object. It may be the first state whose gluonic nature is established strongly enough that the community accepts it as the experimental manifestation of a glueball. That is a mouthful, but accurate statements sometimes arrive wearing sensible shoes. This is why future experiments remain important. More data from BES3 can refine the properties of X2370 and other candidates. Experiments such as Bell 2 may explore related production channels. Proton collisions at high energies may provide additional environments to search for glueball-like states, though with their own challenging backgrounds. Dedicated studies of hadron spectroscopy continue to improve. Theoretical work also advances, especially lattice calculations that include more realistic quark effects and better treatment of mixing and decays. The hunt requires all of this. A detector alone cannot solve the puzzle. A calculation alone cannot confirm a particle. The two must meet, compare notes, disagree politely, and try again. There is a satisfying logic to the kinds of places physicists search. If glueballs are made from gluons, then gluon-rich processes are natural hunting grounds. Radiative decays of heavy quark systems can produce gluons. Certain central production processes in high-energy collisions may favour gluonic states. Heavy ion collisions create environments where quarks and gluons move through an extreme medium before forming hadrons. Each setting has strengths and weaknesses. A clean electron-positron experiment may offer precise reconstruction. A proton collider may produce huge numbers of events, but with a much messier background. A heavy ion collision may create a hot, strong force medium, but then leave an enormous crowd of final particles. The glueball hunter must choose the pond carefully, and also bring boots. The experimental task is made more subtle by the fact that a glueball does not need to decay into something exotic. In fact, it likely decays into ordinary mesons. This is deeply inconvenient. If the final particles were bizarre and unique, the search would be easier. But the strong force tends to produce the particles it is allowed to produce, and ordinary hadrons are plentiful. A glueball may decay into familiar combinations, meaning its exotic origin is hidden behind ordinary products. The final particles do not remember their ancestry in a simple way. They carry statistical patterns, angular distributions, rates, and correlations. Physicists must read those patterns like a language. It is not a language designed for bedtime ease, but it is one of the ways nature speaks. The hunt for glueballs also shows how much trust physics places in absence. If a candidate is not seen strongly in photon-photon collisions, that absence may matter. If a predicted ordinary quark model state is missing, that absence may matter. If a resonance appears in gluon-rich decays but not in other expected places, that pattern may matter. Science does not only study what appears, it studies what fails to appear where it should. A silence in the right place can be a clue. Of course, interpreting silence is dangerous. Perhaps the detector was not sensitive enough. Perhaps the process is suppressed for another reason. Perhaps the model was incomplete. Still, when appearances and absences align across many measurements, a picture can form. What would a convincing glueball discovery look like? It would likely involve a candidate whose mass matches strong theoretical expectations, whose quantum properties are measured clearly, whose production is enhanced in gluon-rich environments, whose coupling to photon-based processes is appropriately small, and whose decays cannot be comfortably explained as those of an ordinary meson alone. It would also require a consistent mixing picture if nearby quark-based states are involved. Different researchers might emphasize different parts of this evidence, but the core requirement is convergence. The claim must survive contact with competing explanations. The particle must not merely look unusual, it must look unusually gluonic. That is why the first real glueball may arrive not as a new particle never seen before, but as a new understanding of a particle already known. X2370, for example, was first observed years before the recent excitement around its glueball-like interpretation. Some scalar candidates have been known for a long time. The discovery may therefore be partly a discovery of identity. We may have seen the object already but not yet understood what it was. This happens in science more often than one might think. The universe does not always hide things by making them invisible. Sometimes it hides them by making them familiar looking. There is something almost gentle in that idea. The first Glueball may not burst into physics as a dramatic stranger. It may have been standing quietly among the mesons all along, waiting for better data, better theory, and more patient eyes. It may be mixed, disguised, and difficult to name. It may require a careful sentence rather than a simple headline. But if it is confirmed, the meaning would be profound. It would show that the strong force can form a particle from its own carriers. It would confirm one of the clearest predictions of gluon self-interaction. It would reveal a form of hadronic matter without ordinary valence quarks. And it would remind us that the substance of the world is not built only from little pieces, but from fields capable of binding, resonating, and becoming. The search is still active because the question remains open in its most careful form. There are strong candidates. There is significant evidence. There are promising interpretations. But the phrase first real Glueball still carries the weight of final confirmation, and physicists do not hand that phrase out lightly. They have learned from too many almosts. Almost a discovery, almost a clean signal, almost a perfect fit. The Glueball deserves better than almost. It deserves the patient convergence of theory and experiment. So the hunt continues through accelerator halls, computer simulations, conference talks, detector upgrades, old data reanalyses, and new decay channels. It continues in plots where bumps may be resonances, in tables where branching patterns may hint at inner structure, in simulations where pure gluon fields produce states that experiments must somehow find in the messy real world. It continues because the prize is not merely another particle name. The prize is a deeper understanding of how force becomes matter-like, how gluons organize themselves, and how the strong interaction builds the hidden architecture beneath ordinary atoms. And perhaps that is the quiet beauty of this search. It is not only a search for something new, it is a search for something that reveals what the familiar has been all along. Every proton in every atom depends on gluons. Every stable nucleus depends on the strong force. The Glueball, if finally confirmed, would be a special case, rare and fleeting, but it would point back to the same physics that makes ordinary matter possible. It would be an exotic whisper from the force that holds the world together. Not a glowing ball of glue, not a tiny sticky bead, a resonance, a pattern, a short-lived knot in the strong field, leaving behind enough evidence for patient minds to follow. And as the search moves forward, the question slowly changes. It is no longer only whether the strong force can make such a thing. The theory has long suggested that it can. The question is where, in the crowded evidence, the clearest trace has been hiding. Whether in the long-debated scalar candidates, in the increasingly intriguing X2370, or in some future state not yet cleanly understood, the first real Glueball will mark a moment when the old boundary between matter and force becomes a little less firm. It will show that the universe can take the carrier of binding, let it bind itself, and produce a particle whose existence is brief, but whose meaning reaches deep into the structure of reality. And from there, the story turns back toward the larger meaning of it all, toward what it says about mass, matter, and the strange talent of the universe for making something solid seeming out of fields that never sit still. And after following the search through detectors, simulations, candidate particles, and all the careful uncertainty that comes with the strong force, we return to the simplest sounding question, the one that was waiting quietly underneath the whole journey. What would it mean for the universe to make matter out of pure force? Not matter in the everyday sense of a stone, a spoon, or the reassuring weight of a blanket pulled up under your chin, but matter in the particle physics sense. A state with mass, a state that can form, decay, be measured, and leave a trace in the world. A Glueball would be exactly that kind of object. It would be a short-lived particle made not from the usual quark ingredients, but from gluons, the carriers of the strong force, bound together by the same interaction they carry. The force would not simply act between pieces of matter, it would briefly become a particle-like structure of its own. That is a very strange sentence when heard slowly. A force becoming a particle. It sounds almost like a trick of language, as if we have taken two categories that should stay separate and quietly swapped their hats while no one was looking. But modern physics has been preparing us for this idea for a long time. The deeper we look, the less the universe resembles a collection of tiny solid objects being pushed and pulled across empty space. That older picture is still useful in daily life. It helps us understand falling objects, rolling balls, and why a mug placed too close to the edge of a table may soon become a small household tragedy. But beneath that level, matter is not made from little hard beads in the way we once imagined. Matter is built from fields, excitations, interactions, and energy arranged in stable or unstable patterns. A particle, in this modern view, is not always best understood as a miniature object. It is a recognizable excitation of a field. It has properties that can be measured. It behaves consistently. It follows the rules. Some particles are stable enough to build the ordinary world. Electrons, protons, and the bound structures they form can persist long enough for atoms, molecules, planets, and people to exist. Other particles are fleeting, appearing only in high-energy collisions or radioactive processes before decaying into more familiar things. Yet fleeting does not mean unreal. A short-lived particle can be as real as a note from a bell. The note does not stay, but while it sounds, it has frequency, energy, and effect. A glueball would be a note played by the strong force itself, a brief resonance in the gluon field, sounding for far less than a moment before fading into other particles. The ordinary matter around us already carries a hint of this lesson. Most of the mass of a proton or neutron does not come from the small masses of the quarks inside. It comes from the energy of the strong interaction, from the motion and confinement of quarks and gluons, from the restless activity of the field. This means the weight of familiar matter is already deeply tied to force field energy. Your hand, resting quietly beside you, is not simply made of tiny heavy pieces stacked together. Much of its mass comes from the dynamics inside protons and neutrons, from quarks trapped by gluons, from energy bound so tightly that it appears as substance. The world feels solid because fields are behaving in disciplined ways. A glueball would take that idea and make it more direct. In a proton, quarks and gluons work together. In a glueball, the quarks would not be the main ingredients. The gluons would do the binding and provide the structure. The carrier of the strong force would interact with itself strongly enough to form a color-neutral bound state. No ordinary valence quarks, no familiar quark skeleton, just the gluon field organized into a particle-like pattern. It would be the strong force turning inward, holding itself briefly in place, then decaying back into the hadrons through which we try to recognize it. This does not mean the glueball would be magical or outside the rules. Quite the opposite. It would be important precisely because it follows from the rules. Quantum chromodynamics, the theory of the strong force, tells us that gluons carry color charge. Because they carry color charge, they feel the strong force. Because they feel the strong force, they can interact with one another. Because they interact, the field can form bound states. The glueball is not a fantasy attached to physics from the outside. It is a possible consequence of the theory working honestly. The difficulty has never been making the idea plausible. The difficulty has been finding the clear experimental signature in the crowded world of hadrons. And that crowded world matters. Nature does not always give us pure objects. A glueball may mix with ordinary mesons, share its identity across several observed particles, or appear in data as a resonance whose meaning takes years to untangle. That can feel unsatisfying if we want a clean answer. We want to point and say, there it is. This particle is the glueball, case closed, tea finished. Everyone may now sleep. But the strong force rarely offers that kind of simplicity. It gives us mixtures, decays, broad signals, overlapping states, and final particles that remember their origins only indirectly. In that sense, the glueball is not only a particle to be found, it is also a lesson in how subtle the word made can become in quantum physics. When we say a glueball is made of gluons, we do not mean it is built like a toy from separate plastic blocks. We mean its dominant structure is gluonic. We mean the field configuration responsible for it comes from gluons binding through their own interaction. We mean its identity is rooted in the strong force itself, rather than in ordinary quark combinations. This is a different kind of making from anything we do with hands. The universe is not assembling a glueball at a workbench with tiny tools and a cup of coffee nearby, though the image is pleasant. It is allowing a field to take on one of its permitted patterns. For a brief time, that pattern has mass and particle behaviour. Then it changes into other patterns. This way of thinking softens the boundary between matter and force. In school, it can be helpful to separate them. Matter is stuff. Forces act on stuff. Gravity pulls matter. Electromagnetism pushes and binds charged matter. The strong force holds quarks together. This division is useful, and at everyday scales it works well enough. But at the level of fields, the division is not so clean. Forces are not invisible strings stretched between pre-existing objects. They are manifestations of fields that carry energy and can have excitations. Matter particles are also excitations of fields. What we call matter and what we call force are different roles played by fields in the structure of the theory. A glueball would show that one of the fields associated with force can produce an object we classify as a particle. There is a deep practicality to this, even though glueballs themselves are not practical objects. They will not power your kettle, repair your socks, or help you remember where you left your glasses, but they matter because they test our understanding of the force that holds atomic nuclei and protons together. If physicists can identify glueballs clearly, they will confirm a key feature of the strong interaction in the region where it is hardest to calculate. They will learn more about confinement, the origin of hadron mass, and the way gluon fields organize themselves. The glueball is exotic, but it is connected to the familiar. The same strong force that may create a glueball also makes ordinary matter possible. This is one of the recurring surprises in physics. The strange and the ordinary are often neighbours. Black holes teach us about gravity, but gravity also keeps your feet on the floor. Neutrinos are ghostly and hard to catch, but they are produced in the sun that warms the day. Glueballs are rare and unstable, but the gluons involved in them are central to every proton and neutron in your body. The exotic is not separate from reality. It is reality seen under unusual conditions. It is the same set of rules allowed to express itself in a more difficult and revealing way. And so, when we ask what a glueball really is, the answer has layers. At the simplest level, it is a predicted bound state, made mainly or entirely of gluons, a particle without the usual quark core. At a deeper level, it is a test of gluon self-interaction and confinement. At a still deeper level, it is a sign that mass and matter can emerge from field energy, not only from little constituent pieces. And at the most human level, it is a reminder that our everyday categories are useful but limited. The universe does not always sort itself according to the boxes our language provides. It allows force carriers to behave like constituents. It allows empty space to have structure. It allows stable matter to be built from motion. It allows something as ordinary as mass to arise from the hidden restlessness of fields. If that feels slightly dizzying, that is understandable. Particle physics often asks us to trust ideas that do not fit into ordinary pictures. A proton is not a tiny billiard ball. A gluon is not a drop of glue. A glueball is not a sticky sphere. These words are handles, not final images. They let us talk about things that are too small, too brief, and too unlike daily experience to picture directly. The real knowledge comes from equations, experiments, simulations, and patterns in data, but the handles help us carry the meaning. and the meaning here is simple enough to hold gently. The strong force is so self-interacting that its own carriers may bind into particles. That is the heart of it. There is also a kind of patience built into the Glueball story. Some discoveries in science are sharp and dramatic, others are gradual. Glueballs belong to the second kind. The theory pointed toward them, calculation supported them, experiments found candidates, interpretations developed, new data refined the picture. The search continues not because the idea is weak, but because the evidence must be strong enough to survive the complexity of the strong force. That patience is part of the beauty. It shows science as it usually is, not a sudden parade of certainty, but a careful process of narrowing possibilities until one explanation becomes the most reliable. And perhaps that is a useful thought beyond physics too. Some things are not understood by looking once. Some things require returning, comparing, refining, and admitting uncertainty without giving up. The Glueball is hidden not because it is unimportant, but because the part of nature that creates it is deeply woven. To find it, physicists must read the weave. They must learn which threads belong to quarks, which to gluons, which to mixtures, and which to the field binding itself. This is slow work, but slow work is often where the deepest things become visible. Now think again of the room around you. Whatever time it is where you are, whatever quiet objects are nearby, all of it rests on the same hidden physics. The atoms in the walls and furniture contain nuclei. The nuclei contain protons and neutrons. Those protons and neutrons are shaped by quarks and gluons. The gluons carry the strong force, and that force is not merely a background detail. It gives ordinary matter much of its mass and stability. Somewhere in the same theory, in the same family of interactions, is the possibility of a glueball, a brief particle made from the force that usually hides inside matter. The world around you seems still, but its stillness is supported by activity too small and too fast to see. This is one of the quiet comforts of science for sleep. Not that the universe is simple, because it is not. Not that every question is answered, because many are not. But that even the strangeness has structure. Glueballs may be hard to find, but they are not arbitrary. The strong force may be difficult, but it follows rules. Matter may be less solid in its deepest description than it appears, but that does not make the world less real. It makes reality richer. The blanket is still a blanket. The cup is still a cup. Your hands are still your hands. It is just that beneath them, fields are doing astonishing work. So if a glueball is finally identified clearly, perhaps in a known candidate, perhaps in a future experiment, perhaps as part of a careful mixing pattern rather than a single pure object, it will not simply add another name to the particle list. It will confirm that the universe can make a particle from the self-binding of force carriers. It will show that gluons, those hidden messengers of colour, can organise into a state of their own. It will strengthen our understanding of the strong interaction, one of the central forces behind the existence of ordinary matter. And it will give us one more example of a theme that keeps returning in modern physics. What looks like stuff is often organised energy. What looks like emptiness often has structure. What looks like force can, under the right conditions, become something particle-like. That is a remarkable thing to carry into rest. The universe is not simply filled with objects, it is filled with processes that can become objects. A star is not only a thing, but a balance of gravity, pressure, heat, and nuclear reactions. An atom is not only a thing, but a structure held by fields and quantum rules. A proton is not only a thing, but a confined storm of quarks and gluons, and a glueball, if seen clearly, would be one of the purest small examples of this truth. The process itself becoming the object, the binding becoming the bound, the force becoming briefly matter. And so we end where we began, with a soft question about what the world is made of. At first glance, it is made of familiar things: wood, water, air, skin, stone, glass, and cloth. Look closer, and those things become atoms. Closer still, nuclei and electrons. Closer again, quarks and gluons, fields and confinement, energy and pattern. Then somewhere in that hidden depth, the Glueball waits as a possibility, and perhaps already as a partly seen reality. A small sign that the universe is more inventive than the simple building block picture allows. It does not always build matter from matter. Sometimes, through the strong force, it may build a particle from the carriers of the force itself. If you have drifted with me this far, through quarks, gluons, confinement, candidates, and the gentle confusion of quantum fields, I hope the journey has been a calm one. And I would love to know, before you go, where are you listening from tonight? Is the room dark where you are? Is it late? Or are you hearing this in some quiet morning while the rest of the world is only beginning to stir? It is a fitting question, because every listener is made from atoms held together by the same hidden forces, each one resting in a different place at a different hour, while the strong force keeps doing its ancient work without needing applause. If this quiet exploration gave you something to think about, or helped the day soften a little, I would be ever so grateful if you liked the video, subscribed, or shared it with someone who enjoys science at a slower pace. It helps this little corner of calm continue its work, one strange question at a time. Tonight, that question was what a Glueball really is, and the answer, as best as physics can currently tell us, is this. It is a possible particle made from gluons, a bound state of the strong force, a fleeting knot in the field that holds the heart of matter together. Not ordinary matter, not simple matter, and not yet fully settled in every experimental detail, but a deeply meaningful possibility. A reminder that the universe does not merely contain forces and things. Sometimes, in the smallest and most hidden places, the force itself may become the thing. Sleep well, fellow traveller, wherever you are and whenever this moment has found you. The atoms round you are quiet, the fields beneath them are not, and somewhere inside the rules that hold the world together, the strong force may still be whispering its strangest little trick, that even glue, under the right conditions, can become something of its own.